to give you some of the basis of the mathematical basis that will be useful throughout this tutorial. Then I will move to the hands-on section. First, we will implement the first FDS model without using the library. This to understand the basic principles of finding different schemes in Faust. Then we will have a brief look to the
This is another test.
Salut Romain, ça va? Est-ce que tu m'entends, Romain? Salut Romain, ça va? Est-ce que tu m'entends, Romain? Est-ce que tu m'entends? Pour l'instant, je t'entends pas, mais c'est peut-être normal.
Ouais, tu m'entends là?
Ah, mieux. Beaucoup mieux.
Bon, en fait, c'est juste qu'il y a plein de sessions en parallèle de plein de trucs et que,
Ouais, j'imagine.
du coup, ouais, j'essaie de faire au mieux.
Pas de souci.
C'est pas évident. Attends, je réfléchis à.
Moi, je t'entends bien. Par contre, c'est bizarre, j'ai une version de ma voix avec un délai énorme.
Okay, well, hi everyone. First, I hope you can see me. If there are any technical difficulties, please let us know directly in the chat on YouTube. We're a little bit in advance, but I thought that I wanted to give you a couple of information before getting started on the first workshop today. So if you have any questions throughout the workshop, I invite you to just ask your questions directly in the chat on YouTube, okay? And then, as you probably recall, we sent you a link to a Google Meet where you can actually interact with presenters after their presentation is over. So yeah, please ask your question in the chat. If there's time left at the end of presentations, presenters can try to answer your questions. But otherwise you can keep conversations going after the presentation is over. So yes, today we have a pretty busy schedule, and I'm sure you already know about it. So most of the presentations you're going to see today are pre-recorded. So you'll just have to to follow the tutorials, and once again there will be live Q&A sessions after each presentation. We'll have a break for 1 hour at 6 p.m. Local time, so French time, GMT +1. And yes, and then we'll keep things going until 9 p.m. Tonight. So I think we're ready to go with the first presentation. Once again, if you have questions, feel free to ask them in the YouTube live chat. And welcome everyone. Thanks for attending this workshop. And the first presentation, the first tutorial will be by Dirk Rosenberg, who's gonna present his his wave digital filter library in Faust.
Hi, I'm Dirk Rosenberg. I'm a current undergraduate student at Oberlin College and Conservatory, and welcome to Modeling Analog Audio Circuits in Faust. In this workshop, I'm going to introduce the technique of wave digital modeling using the library which I've written, wavedigitalmodels.lib, which supports creating wave digital models in Faust. Hopefully, this workshop will be targeted at anyone who is interested in the modeling technique or analog or virtual analog modeling in Faust. We're going to discuss a couple of simple circuits, and also towards the end discuss some of the more interesting challenges and associated with implementing complex wave digital models in Faust. So first, let's start with just what is virtual analog modeling. So the virtual analog modeling is the answer that arises out of the question, how does one simulate an analog audio circuit in the digital realm? And the first sort of step that you might take is something like black box modeling, which is basically looking at your circuit and its behavior completely irrespective of anything that you might think is going on inside it. This would involve something like taking impulse responses of the circuit or doing sine sweeps, trying to figure out what the output characteristic of the circuit looks like based on the input characteristic, and then modeling that directly using simple DSP elements such as biquads or oscillators or simple things like that. Another perspective is white box modeling, which involves analyzing the behavior of the circuit itself, creating a physical model from that, digitizing that physical model, and then using that physical model in real time to compute the characteristic. White box modeling includes techniques such as transfer function analysis, wave digital modeling, and state space models. In which you're actually using the Kirchhoff laws that describe the circuit to create a model that can then be. So ultimately, what we're trying to create is a model of the entire circuit's behavior. One of the really cool things about wave digital modeling is that it's actually a modular approach, in that instead of just with something like transfer function analysis, where we try and derive the entire behavior of an individual circuit, instead with wave digital models, we're going to try and work as discretely as possible to digitize individual components and then have them have congruent parts in the final model. And this is really beneficial because it means that it's much easier to change or modify the digital model without having to rederive everything associated with it. So with wave digital modeling, we can almost take a math light approach to analyzing these circuits. But here on the left, we have a second order passive low pass filter, which is just formed with two resistors and two capacitors in a ladder structure. And this is the kind of circuit that wave digital models were originally created for. On the right here, we have our wave digital model, which is a collection of nodes which have waves traveling between them. You can see that nodes might have one connection to another node or several, but what's happening is each node has some connection to an element of the circuit, and these nodes are derived based on the individual elements' Kirchhoff relationship. And digitized here, we see really two things, and this is a core aspect of wave digital filter or wave digital model theory, that components and their connections are derived separately, where each resistor has an individual node, and then they're connected to other nodes which describe the resistor's connection to the other circuit elements, rather than having a resistance node being connected to say exactly what the resistor in the schematic is connected to. So one of the major problems here is this is what the implementation of this final circuit looks like in Faust. And this is a, frankly, very, very bulky representation. And coding something like this manually would be very painful. You lose almost all of the desired modularity that you get with wave digital filters. So what I've been working on is a library which really greatly simplifies the process. And we can actually declare this entire model in just a couple lines of code, basically just by declaring our nodes, which correspond to pre-written functions in the library, which have already digitized the resistor, the capacitor, a voltage source, etc. And then we connect them together in a data structure called the connection tree, which then is sent to other library functions, which will inspect the connection tree and build the final model. And it makes creating these models quite easy and straightforward. All right, so now I'm going to demonstrate the code that I've just showed you in Faust. So here we can see this is, we're just grabbing from the standard, Faust libraries, which already include all the adapters from wave digital models. We use the prefix WD to access all of the various functions. And then we're just going to create our circuit, which in this case is a second order filter. And if you see the corresponding things when we call our model, we're doing a resistor, two resistors of 47K each, and then 47 nanofarads for our two capacitors. And if we run this, let me just add a little bit of code to make this nice and stereo. And then what I'll do is I'll declare as an input no dot, just grab a simple white noise function. And if we listen, pass a signal comparison. over, we'll get a little bit of a description of what's going on with the node itself, including some detail and reference information in case you're interested in learning more about the node itself. The same is true for functions like the build function, and as well as connection nodes inside the connection tree. Returning to our wave digital model, let's talk a little bit about how this model itself is created from the circuit, because it's not immediately obvious. This is a simple enough case that we can do it pretty much by inspection. Those of you who are a little more familiar with circuits and electrical engineering would sort of notice the immediate topology of this circuit in that it's a resistor and a capacitor connected in parallel with a capacitor, and they're connected in series with a resistor and a voltage source. Very simple. And that is what's happening here. We have a capacitor and a resistor connected in series, connected in parallel to a capacitor, and then that's connected in series to a resistor and a voltage source. Taking a look at this rearrangement of the circuit, it becomes a little more obvious, where what we've done is we've pulled out all of the components of the circuit, which would be things like our voltage source, our resistors, and our capacitors, and enclose them in their own boxes. Then we also have boxes which enclose topology. And these specific topological connection boxes correspond to the series node and the parallel node. And that's really how we get this final wave digital filter structure, or wave digital filter, wave digital model structure. So another thing to be clear about, I mentioned earlier the connection tree data structure. And that has also an associated derivation. The connection tree is how the wave digital model is represented such that it may be computed easily. The reason why the wave digital model looks the way it does here is because this directly corresponds to the connection tree thing, where we denote a specific node to be our root, and then we have internal adapters, which denote the connections. And then we have leaf nodes and the root, which denote components. And here, for example, node 2 corresponds to R1. So let's talk a little more about what's going on with our implementation here in Faust itself. There are really three distinct parts. The first thing is declaring the nodes, which is basically we have specific resistances, specific capacitances, specific voltages that are going to be applied within this circuit. And we need to declare the nodes which correspond to those. The second of which is declaring the connection tree, which is the data structure which I've been talking about. And then the last one is building the model itself, in which you pass the connection tree to one of the library's build functions, which inspects the connection tree and creates the final model. So first of all, let's talk some specific syntax just for using the library. Nodes are declared just by creating a function which is equal to one of the library nodes. For example, Wave Digital, creating a resistor, you use the wd.resistor thing, and this will create a resistor which has the component value R1. All of the library nodes have various parameters which allow you to govern exactly the values or gains or associated complexities with those nodes. There are also a couple of different kinds of nodes. The resistor here is a regular node. Here we have an unadapted voltage node. And I'll talk a little bit more later about what unadapted versus adapted means. And then the last one is the library also has separate nodes for components, which you want to take the output of your model from. So for example, in this one, we want our output to be the voltage across capacitor 2. So we declare, instead of just declaring it a regular capacitor node, we declare it a capacitor underscore output node. Another thing that is really important here when declaring nodes is that you leave this build function parameter unparameterized. This is something which is used by the build functions in order to create the connection tree, and you have to declare nodes of this form. And all of the nodes to the connection tree must be of this form as well. Another important aside, it might be tempting to do so, but you cannot use the underscore or empty signal operator to declare a component's value. There are tons of ways in which we can get signal into our models, and I'll talk about those a little bit later, but it does not work to use the underscore. That actually often will break the model. The last sort of node which I wanted to mention is we have topological nodes in the library. You can just simply use them in the connection tree as you would any other node, or if you prefer, you can also declare them of the same form up here. Faust does not have a built-in method for declaring tree data structures. So the library uses its own metaprogramming representation of tree structures. And to do this, we use two things, the sequence operator and parallel construction. The sequence composition operator denotes a connection between two nodes or multiple nodes. Typically, this is traversing downwards in the tree. So for example, our node 1, vin, is connected directly downwards going to a series. So you can see we have vn connected to the series. The other thing is that when you want to connect a node to multiple downward going nodes, as is say with like S2, what you're going to do is use parallel construction for the downward going nodes. So for example, with the with the series operator, the last one, S2, that's connected to R2 and C2. So you just simply declare R2 and C2 in a parallel list, and then apply the sequence operator, and that denotes their connection. So last thing to talk about in terms of syntax is building the model. So once you have your connection tree data structure, what you do is you pass it as a parameter to one of the build functions. There are a variety of these associated with it, but most often you want to use the build tree function, which will automatically inspect it, create all the outputs, create all the inputs, do all of the recursive composition automatically, and set up the full digital signal processing structure without too much input. Another thing that's really important and that I would recommend as a coding practice is to declare all of your components and your connection tree within the scope of a model. This is really helpful because it allows you to fill various component parameters, which is something that you must do. You must fill all the component parameters, as we talked about, I think 2-ish slides ago, in order to build the function. And also it allows you to declare things like inputs. Here I've pulled all of the relevant component constant quantities out into our parameters so that we could modify them if we wanted, though you could declare them explicitly within the model as well. Another thing which I recommend is to leave any desired signal inputs as the last parameters, because in this way you can use them explicitly within your component declarations and then just simply leave them unparameterized when you call the model in your Faust function. And in this way, Faust will automatically treat the function as a parameter or an abstraction, and then your signal will be routed all the correct places. This is how you can create models with signal input rather than using the empty signal operator, which, as I previously said, should not be used for component parameter declarations. All right, so now that I've gone over some more of the syntax, let's go ahead and take another look at our second order filter and do something a little more interesting with it than just having to do all of this. So instead, for a second order filter, I think it would generally be helpful to, instead of having it be in terms of all these resistance and capacitance parameters, let's just make this in terms of a cutoff frequency F0. Now, what we need to do is provide the relevant values for our resistors and capacitors, which will do this. So first of all, let's just say that our resistors are going to be equal. So we'll go ahead and say R2 equals R1. And then I'll also say, we'll just set them to a constant value. 1K is a good choice. Next, we need to declare our capacitance values. And resistance in circuits is constant with respect to frequency. But we want our capacitance, in order to behave based on a cutoff frequency, it needs to be inversely proportional to cutoff frequency. So again, let's just go ahead and set our capacitors to be equal. And then let's say C1 is going to be equal to 1 over our cutoff frequency, F times, in this case, for correct things to work, what we're going to want is 1.662 times 10 to the negative. And this has to do with just the electrical characteristics of the circuit itself. Hang on, I need to fix that, I think. Okay, so I'm getting... Oh, yeah, I'm applying too many parameters. So now let's go in and say, okay, well, we want a cutoff, a filter with a cutoff at 1,000 hertz. And now, hopefully, but now, since we just have it in terms of a cutoff frequency, and you'll notice I'm doing the trick that I talked about earlier, which is declare our constant parameters first, and then our signal parameters later. Let's go ahead and make this in terms of, let's say, a horizontal slider of V, what would it be? We'll call this cutoff frequency. And we'll start this at 1,000. It'll go down to 20 and up to 20,000. And we'll do it in increments of 1 hertz. And now, if we run it, we have a filter controlled by a slider. Alternatively, we could do something like make this a signal controlled filter, which will control it based on an input by doing it, just leaving this parameter also empty and then feeding, say, like a ADSR envelope into this. One thing that I would really recommend is this does behave very similarly to a normal circuit, in that what we're affecting here is our actual capacitance values. So if you were to do something like to feed in a negative capacitance, it wouldn't necessarily make sense to the circuit, and the model may not necessarily behave in the way that you expect, because that doesn't really equate to a physical property that could exist in this specific circuit. For this reason, I would sincerely recommend performing some level of input protection on your capacitances and values. The first one that I would recommend, since we're going to go ahead and add to F0 just about 0.001 hertz, since this will have very little effect on the actual cutoff frequency, since it's not that exact of a value anyways, but it'll make sure that we never have a divide by zero error if we were to input a zero frequency. And the other one that I would recommend is to do absolute value of this, such that it won't ever go below zero and create an error that doesn't really make sense. If you want to play with these things, obviously you can, but it means that the model might not necessarily obey the physical properties that you would immediately expect. Something which I haven't talked about yet is the idea of adapting, which is the process which eliminates delay-free loops within wave digital structures. Again, when you have waves traveling in multiple directions, especially when you have it's very easy to create loops. And in wave digital modeling, you must manipulate free parameters of the model such that there are no delay-free loops. This process is, as I mentioned, mostly taken care of already by the connection tree, but it is really important that the connection tree be properly formed. And to do that, you really only have to do two things, which is make the root of your connection tree an unadapted node, and then all of the other nodes within the tree must be adapted. If you try and create a connection tree in the library which doesn't follow these rules, it's very likely to create errors. So to talk a little bit more about adapting, like I said, it's a manipulation of a free parameter called port resistance. The library takes care of this process already by automatically setting the port resistances as they should be. Specific circuit components cannot be adapted. They don't have a manipulatable free parameter that can create this desired non-reflective capacity. This occurs in particular with ideal linear elements and also all nonlinear elements. With ideal linear elements, we can simply just approximate these. So for example, while an ideal voltage source cannot be adapted, it can be approximated by using a resistive voltage source with a very, very small resistor in series with it. This is in particular a problem with nonlinear elements, because nonlinear elements cannot be adapted. This means that in a circuit, with the current model presentation that I've shown, we can really only have one nonlinearity, and it can only be a one-port nonlinearity or have one downward-facing connection. This is obviously inconvenient because something like a transistor or a vacuum tube would require multiple port connections. Regardless, we can definitely, just with the theory that we've worked with so far, do diode simulations, which are still a simple one port. They're unadaptable, so it will have to function as the root of our connection tree. But if we only have just one diode, or there's a specific case which has been solved where you have diodes in anti-parallel and even multiple diodes in anti-parallel, which can just be resolved to a single node. And this is really cool because this is a case that occurs in the clipping stage of the Ibanez Tube Screamer. For those of you who aren't familiar with it, it's a very popular guitar distortion pedal which uses diode clipping in order to generate distortion. This particular wave digital model is just simulating the distortion stage of the circuit. And you can see this is actually a little different from some of the models that we've taken a look at so far, in that it's occurring in actually a 3-stage process. This isn't anything special about wave digital models, but is actually a breakdown of the specific op-amp construction that you can find in circuit theory. Where it's broken down into 3 distinct stages for this specific inverting op-amp style. And you can see what we get is 3 distinct wave digital models in which we have 3 different connection trees associated with them, and you can see the root is the grayed out box. Returning to our Faust IDE, you can see that our code is growing in size a bit, but we're still mostly just using built-in library functions, declaring all of the different 3 stages, as we saw earlier, in different sections, and then linking them all up in a final model. You can see here we're using the diode anti-parallel node in the C stage, which takes as an input a saturation current and a thermal resistance, as well as the number of diodes in forward and backwards configuration. And then we'll simulate that node using a custom written Lambert function solve. Other than that, pretty much the construction is all the same that we're seeing here, where we have specific capacitor and resistor values, voltage sources, a resistive voltage input, and pretty much that's all that's going on here. You'll notice here that in addition to just the simple wave digital models, which are all encompassed in stage A, stage B, and stage C, we also have added input protection and on state. These are additions which I talked about. These are in line with what I talked about earlier, in that this is attempting to simulate a physical circuit and providing, say, an input voltage that is much, much greater than what the circuit would expect would have the effect of physically sort of blowing up our digital model of the circuit. Obviously, in the digital domain, we don't have that kind of risk because we can just simply reset our simulation. But in particular, with the diode anti-parallel, a diode is an exponential nonlinear element. So if we try to press an incredibly large current through or an incredibly large voltage across, the diode will explode. And that's what happens with this function. If I were to remove the input protection, you'll see that we can actually go get so large of values inside of our model that it would go past the limit of a float in Faust, which is very large, and explode to effectively infinity or not a number. So in order to do that, I've added some input protection, which prevents levels going above a certain level on the input, as well as some gain correction. In particular, if it's a guitar pedal, it's going to expect incredibly small voltages on the input. So you'll notice that I'm reducing the initial gain of the input signal by a lot, since we would expect only a couple millivolts on the input, but we would be accepting just numerically from the digital process, probably between -1 and 1 on the input. So I'm going to go ahead and run it, and I'll use this audio file. And what we have here is an on, which is representing the bypass for our pedal. And if we turn it on, we get a little bit of a gain boost, but mostly we're just getting distortion. And this is not the regular square distortion. This is actually based on the diode itself. And if we reduce it, our distortion, increase our distortion. And these UI controls correlate to controls on the pedal. Those of you who are familiar with the Tube Screamer are probably wondering where the tone control is, and that's part of a different portion of the circuit, which is not simulated with this wave digital model. I'll go ahead and input a 440 sine wave, and if we look over here, we can take a look at what our distortion character looks like. And you can see we're actually getting the diode-like distortion of the soft clipping rather than the hard clipping that you would see in the digital domain if we were to exceed the bounds. Which, by all accounts, I think is pretty cool. The last portion of sort of modern fundamental wave digital model theory that I want to cover is something called SPQR tree decomposition, which is a more mathematical process for determining the exact connection tree. In particular, once we got into more complex circuits, it becomes very challenging to just sort of inspect the circuit and know where we want to place the adapters. So instead, we perform an inspection of the circuit's graph, break it down into component parts, form a tree, and then this is what the wave digital model will look like. So to get a little bit more in depth, what's going on here is, for those of you who aren't familiar with a circuit's graph, a circuit graph is a graph of the circuit in which each edge corresponds to a component in the circuit, and each node corresponds to a wire or connections between the components. You can see here, edge 1 is corresponding to our voltage source, edge 2 is corresponding to our resistor 1, and node A is corresponding to the ground wire here, which connects the bottom of our voltage source, the bottom of the capacitor, and the bottom of the other capacitor. Decomposing this, what we do is look for edges which are in series or parallel. Specifically, what you do is look through the graph and remove sets of nodes to see if this breaks the graph into two pieces. So for example, if we look at nodes 4 and 5, if we were to remove their connections to C and A, that would break the graph entirely into two separate pieces. So what we do is we break the graph into two separate pieces and then draw a virtual edge along this and along the connection between 4 and 5. So you can see here what that looks like. Here, edge 3 has a virtual edge 2' drawn along it, and then we see the same 2' edge drawn from components 4 to 5, and they've been separated into two pieces. You perform this process until it can no longer occur and the graph has been broken down into fundamental structures which can no longer be represented with more simple structures like series and parallel. And what we're left here is a set of graphs of generally three different types. Series, corresponding to S, parallel, corresponding to P, and one that you don't see in this specific structure called rigid. In our wave digital filter, this is going to correspond to our series nodes and our parallel nodes, and again, not seen here, our rigid nodes. The tree structure, what you're going to see is all of the original edges become nodes. We denote, in this case, node 1, which is our voltage source, if you remember, as our root node, and then all of the other components become leaf nodes 2, 3, 4, and 5. Then internal to the tree are connection nodes, series, parallel, series, rigid, etc. And then inside of the tree, they're going to be connected by virtual edges like 1', 2', etc. You can see here, if we look, we denoted this as our series node, and it still retains the same connections, edge 1, edge 2, and edge 1'. You can see edge 2, edge 1, and edge 1'. Then this circles all the way back to our final wave digital model in which the voltage source is the root. Then edge 2, which has come through the process here, and it started out as R1, is R1 again. So this is important specifically for the decomposition of more complex circuits, as I already mentioned, which cannot be decomposed into always the simplest adapter types. For example, here you see a rigid adapter in which we can no longer remove any edges or remove any connections to nodes and separate this graph any farther. The edges are rigidly connected. The problem here is that there are a great many different possible types of rigid adapters, and they must be derived separately to be implemented in a wave digital structure or a wave digital model. Now, it's not really within the scope of the workshop to talk about that derivation process. If you're interested, I would encourage you to check out the paper referenced below, where the figures are from. But I am working to actively support these kinds of adapters in the library itself. And this is really important because these adapters can be used for doing things such as op amps. So this circuit specifically is the Fender Bassman tone stack, which is the equalizer circuit that you see on the input of the Fender Bassman guitar amplifier. So here in our Faust IDE, we have the 6-port scattering matrix, which is associated with the rigid adapter found in the Fender Bassman tone stack. You'll notice that I've left 6 resistances as parameters, and these are our upward facing port resistances. The input to this function is treated as a 6-element vector, which is then left multiplied by the scattering matrix. To support the easy creation of other scattering matrices, I've implemented several generic node functions. Here, since we're using it as the root element, we use the U underscore, which is the unadapted prefix. It will automatically generate the associated node for the wave digital structure. It is expected for this function to have, for example, for a 6-port scattering matrix, it's expected to have 6 parameter inputs for the upward facing port resistance and also 6 inputs for the incident waves, and it will give 6 outputs. Other than that, this is a direct implementation of the model I showed earlier, where what you can see is we're using our U_6 port as the root of our tree. It is downwardly connected to 6 subtrees, all of conventional wave digital filter structures. You'll notice here I've set up a couple of potentiometers, which are representing the potentiometer values which would be found on the Fender Bassman tone stack. And then I'm also adding a little bit of resistance where necessary in order to prevent zeroing out, which would break the model itself. Having, for example, a resistance that is 0 will create divide by 0 errors in the model and break it. So if we run this, I'll go ahead and demonstrate just using some pink noise a little bit. And presumably, if you were to, say, input your guitar signal into this, it would behave very similar to the actual Fender Bassman tone stack. So the last thing that I want to get into a little bit before going into sort of some of the more advanced aspects of the library's internal logic and functioning, I want to talk about sort of the capacity to circuit bend in Faust, because that's really one of, in my mind, the coolest things about this library. So Faust is very functional and very modular on its own, but I've also really tried to work to make it such that the library can do that as well. I've already talked a little bit about this with the first filter that we looked at, say, making it be a signal controlled filter just by leaving the cutoff frequency as an empty input. But you can also do things like just mess around with the wave digital structure as well. Any unadapted node can be substituted with any other unadapted node. Any adapted node can be substituted with any other relevant adapted component node, etc. As long as the number of connections within the tree and the rules of the connection tree are continued. Similarly, if you wanted to change different aspects of the circuit, that's really easy to do. Any single component can have anything as its component value as long as it's declared explicitly. If you wanted to make a function that an inductor that has, say, a sine at 1000 hertz, that's perfectly legal to do. And honestly, I have no idea what this will sound like, if it will even sound like anything. Well, looks like we broke the model itself. Oh, that's probably because it's going below 0, so I'll just do absolute value plus 1. There we go. Sure, that's I'll do plus 0.0001. Yeah, that sounds reasonable. And now, it didn't impact functionality as much as I expected, honestly. I can't really hear anything different with it, but again, you might run into very strange cases or things like that. The other thing is I've created a set of functions which are going to be published with the next iteration of the library, which can pretty much take any node or take any Faust function and turn it into a library node, provided a couple of different things. Now, there's going to be more documentation on these functions coming out, but this sort of gives people the capacity to really turn anything into a node. This is something which I hope people have the opportunity to break and mess around with in very strange ways and create some really cool stuff. So to get a little bit more into the advanced functionality of the library, I want to take a look at exactly what's going on. So generic nodes are broken down into 3 different cases. You can see here we're accessing our first index, the index parameter, which is accessed by the compiler, and we're declaring 3 different portions based on the scattering matrix of the node. So in wave digital filter theory, nodes are classically defined by a scattering matrix, particularly adaptable nodes, and various properties of this scattering matrix will denote whether the node is adaptable or not, etc. And really all the library does is break them down into 3 different portions. One of which computes the upward going waves, one of which is the 1 case, the 0 case computes the downward going waves, and then the 2 case will feed the upward facing port resistance of an element to the library. So I'm going to go ahead and return to our simple model, or our simpler model, and I'm actually going to make it even simpler here by going ahead. I'm going to remove R1 and C2, and then I'm going to just condense down to R1 and C2. So this is now a first order, I believe. That should be the correct number. And now we're reduced just to a very simple model. So here, what you can see is the series, our 3 port, which is the wavedigital.series node, is broken down into 2 different portions, a downward portion and an upward going portion, each of which is fed the up port res, the upward facing port resistance, which is computed automatically from our R1 and C2 values. So this is how we achieve the automatic adapting properties of the library, and similarly, our voltage input is also automatically fed an upward facing port resistance, which uses the series, which is R1 plus R2, as well as this to automatically compute upward-facing port resistance. Similarly, this is automatically doing routing. You can't see much of it here, but we have basically, instead of having waves going up from C1 to C2, they go all the way around. And this is where our unit delays occur and that eliminate the delay-free loops in our final model. So to take a look at our build function, what's actually going out here, the function build tree, which builds the model, is taking our model as an input in the form A:B, and it's going to build the downward going part, which is this portion, and then it's combined recursively with the upward going part, which is this portion, and then also the out generates a crossover, which will eliminate all of these signals, the state vectors, from being fed forward. What we're doing is recursively inspecting each level of the connection tree, and then from it generating a node's upward or downward going element, the inputs to which are either are the relevant values and the upward facing port resistance, which is generated again through another inspection. And then finally, some extra crossover steps, which will deal with any necessary signal routing, which would be an issue otherwise. We're using a lot of advanced pattern matching functionality in order to generate these things. Even the crossover is just a very, very advanced pattern matching function, which again will generate a proper crossover based on various aspects of the tree. If these are things which are interesting to people, I'd be more than happy to talk about them in a bit more depth, perhaps in the Q&A if people have specific questions. But hopefully these are things which will have very little impact on just use of the library and are more about interesting aspects of wave digital models in Faust moving forward. One of the really cool aspects of Faust is that this results in purely instructional code, which is to say that there's no tree traversal in the final code. There's no loops. It's just a set of ordered instructions for computing the behavior of the model. Effectively, all of the computational intensity associated with the connection tree itself is front-loaded into the Faust compiler, which is capable of just inspecting all of the relevant elements and then creating the final resulting instructional code itself. I'm still working on doing tests to figure out if this is substantially faster than existing methods for implementation, in particular comparisons to Max Rest's C++ library, RT-WDF, which you can find on GitHub. Finally, I just want to go over what I'm hoping to do with wavedigitalmodels.lib in the future. Hopefully, at the time of publication, the additions listed in the 0.2 will be live and available to everyone, but it may be as long as a week or two before these go completely live, just simply for reasons of checking and confirming that everything is correct. And that's going to add a bunch of stuff, especially R-type adapters for simple cases. So for example, the tone stack adapter will be available, as well as some adapters for op-amps, I hope, which will allow people to do simple op-amp configurations without having to redo a ton of work. And Also, the generic node creation functions will be made available in that library. And finally, the documentation, which I mentioned earlier, which will hopefully make things prettier, more readable, and fix some errors and typos that were present in the current version. And then in terms of future editions, I'm really hoping to publish the scripts, which I mentioned, which will help derive R-type adapters so that folks who don't want to deal with the extensive math associated with their derivation will be able to hopefully do that a little more easily just by knowing the circuit's graph. And the other thing, additionally, I'm really hoping to develop, and this is something that's in active development right now, is internal functions for multi-port nonlinearities. Basically, once a user has an R-type, I'm hoping to provide a different build function which could, example, add like a tube to your R-type or add a transistor to your R-type, or add multiple diodes, things like that, which would allow for basically really easy modular use of these elements, which is something that hasn't really been available in the past. I'm really trying to focus right now on expanding library functionality, but soon I'm also hoping to publish examples. As I'm working on more complex things, I will definitely publish the results so that people can modify or circuit bend as they are interested in them. So finally, just a couple of details on references. For general knowledge, I would really encourage you to refer to Kurt Werner's thesis, as well as his IEEE papers. They've published a lot of the techniques that I've talked about, and I use them as a direct source when creating the library and dealing with issues and learning the technique myself. For the Tube Screamer specifically, I've already mentioned this, but the improved and generalized diode Clippard model paper. If you're interested in checking out a modern implementation example, I would really recommend the Zhang paper, Real-Time Digital Simulation of Cascaded Vacuum Tube Amplifiers Using Modified Blockwise Method. It's a really interesting advanced look at applications of these techniques. Many of these techniques are just completely developed as a result of DAFX, and I would be totally remiss not to mention that conference. I have read many DAFX publications in creating this library and would really encourage anyone to read those publications if they're interested in this technique. There's wave digital modeling stuff that's really recent that just came out in August, which is detailing new work on these techniques, and there's really amazing stuff being done by tons of really cool people all over the world in this. And then finally, many thanks to Romain Michon and Graham, especially for allowing me to present my work and this library as an undergraduate. I really appreciate the opportunity. Also, many thanks to Kurt Werner, who really directly has supported me in learning wave digital filters. Julia Smith as well. I've really appreciated all of the help and encouragement. Also, the Faust Slack, who was invaluable in working to answer some of my more weird questions and weird bugs that were encountered when developing the advanced aspects of the library. And finally, many thanks to Rob Owen and my advisor, and Eli Stein, my private teacher, as well as Oberlin College. Thank you very much. And I will hopefully be in momentarily to answer any questions that you have.
Okay, I think it should work now, actually. Yeah. I think it should work. So are there any questions, Dirk?
Yeah. I don't see anything in the chat right now, but I wanted to expand briefly, I guess, while people are thinking of questions on the multi-port nonlinearities problem in Faust. For folks who are familiar with wave digital filters, this is at least the thing that I've investigated right now is Kurt's treatment, which involves the integration of the multi-port nonlinearities into an R-type adapter. But I wanted to expand. Oh, okay. Getting a little bit of feedback. Okay, we're good. But sorry, lost my train of thought briefly. Yeah, so in Faust, this totally should be possible. The one thing that is sort of an active question right now, as far as I know, there isn't a great way to do the lookup table method in Faust. And in particular with Faust, because Faust code is non-Turing complete and can't have internal loops, you have to do a set number of iterations for resolving the problem associated with the zero delay stuff. So it's sort of, I'm actively investigating how to work at integrating these nonlinear elements like tubes and transistors with this problem of how to successfully use iterative methods like that in Faust to resolve these like big problems. Yeah.
Cool. Well, thank you, Dirk. I'm sorry, but I think we actually have to switch to the next presentation. Once again, if you want to ask more questions to Dirk and actually talk to him directly, you guys can switch to the Google Meet chat if you actually want to talk with Kurt. Okay, so the next presentation is going to be by James Leonard, who's going to talk about mass interaction physical modeling in Faust. Thank you, Dirk.
Thank you.
Hi everyone, I'm James from Gypsylab in Grenoble, France, and my workshop today is going to concern mass interaction physical modeling within Faust. So what is mass interaction physics? Basically, when you're looking at solving a physical system in classical point-based mechanics, like you might have done in high school, for instance, you describe a physical system as being composed of a number of simpler entities that are coupled together through some interactions of some sort. So you might have a punctual mass here, another one here, maybe something over here. You could have a spring that couples two masses together through Hooke's law. You might have some gravitational pull or any other kind of interaction force. And all these things together will give you a system of partial differential equations. And if you take all that and you solve it, you can obtain what you're looking for, such as the motion over time of one mass in the system, for instance. And that's exactly what we're going to be doing with our system. So if we look at how this compares to other types of physical modeling, in modal synthesis, for instance, what you would do is mathematically describe all the vibration modes of a generally linear physical structure. So you'd basically say you have a string or a plate or something, you'd figure out all the vibration modes for this real mathematical object. And once you have that, you can basically just resynthesize all the vibration modes through additive synthesis and then obtain something that basically behaves in the same way as the physical object would. Whereas in waveguide modeling, for instance, you'd approach things differently by representing motion as traveling waves, basically two traveling waves in opposite directions that represent basically motion within a given medium. And then you'd add scattering junctions and things like that to account for places in your system where some waves might be reflected back or transmitted forward, and so forth. And finally, in finite difference schemes, what you do is take a certain physical system as a point of reference, say a string or a mesh or something like that. You'd describe the continuous system for this physical entity. So for a string, you'd use the one-dimensional wave equation. For the mesh, you'd use the 2D wave equation, and so forth. You'd define some boundary conditions for this system. So where is the wave going to bounce back on borders and things like that. And once you've completely described this system as a continuous physics problem, basically, you'd look at ways to best discretize this system to solve it numerically. And what we're doing in mass interaction is kind of a step back from that, in that we discretize the basic physical elements upstream, if you will. So we're going to have a discrete time mass, a discrete time spring, and all sorts of other interactions and things like that. And then what we do when we have these things is we can just assemble them together to build physical networks, basically, and do what we want. It's interesting also to note that there are many equivalencies in basic cases such as strings or meshes and things like that. You can find mathematical equivalencies between a lot of these different approaches, and I'd refer you to Stefan Bilbao's book on numerical approaches to sound synthesis to have a deeper glance at that. Mass interaction modeling first came to be at Acroé in the 1970s, and mainly through a concept and a formalism called cordis anima, which defines the ground rules, if you will, for mass interaction physical systems. And that's given rise to software such as Genesis and Mimesis, and along the years gave rise to many other people finding an interest in mass interaction modeling and developing their own ideas and their own tools. And that ranges from Tau and Cymatic to PMPD, which is physical modeling in pure data, all the way to HSP, haptic signal processing, and to Synthemodeler, which was designed by Edgar Bedal in Faust, and which is quite similar in many ways to what we're going to present in our work. So now I'll quickly cover what we at Gypsylab do in regards to mass interaction physical modeling. And for that, you can have a look at the MI Creative website, micreative.eu. And here you can find all the work that we conduct regarding mass interaction physics, be it for Faust, for MaxMSP, and for specific art science projects. And within this, we're going to start with the paper that we published at the Linux Audio Conference in 2019, entitled Formalizing Mass Interaction Physical Modeling in Faust. And what this paper gives is a kind of general framework of how the basics of mass interaction physics work and how we can implement them in Faust. So if we look at it here on the screen, the motion equation for a continuous time mass would be given by Newton's second law, quite simply, as F equals ma, F being the force applied to the mass, m its inertia, and a its acceleration. And so that naturally means that m equals second derivative of x over dt, so the second derivative of position over time. And if we want to find a way to basically give ourselves a kind of a state equation in discrete time for this system, what we can do is apply a second order central difference scheme to the variable x above. And what's that going to give us? It's basically going to end us up with this this state update scheme wherein x of n plus 1, so that the new position of a mass is going to be equal to 2 times x of n, its current position, minus xn minus 1, which is the previous position of the mass, so you have the velocity of the mass in there basically, plus Fn, which is the force applied to the mass in the latest time step, divided by m. And m here is the discrete time inertial parameter, and it's defined as the continuous time inertial value divided by the sampling interval squared. So that's something we kind of have to keep in mind. And if we go a little further and look at how a spring could be approached in discrete time, well, if we look at a linear spring that obeys Hooke's law, you'd have something that generates force which is equal to minus k, which is the stiffness value, times x2 minus x1, x2 and x1 being the positions of the masses connected by the spring. And since there is no kind of temporal or memory aspect to this interaction, it's just a continuous equivalence, basically, this can just be discretized immediately. So equation 6 here gives the discrete time version of this. And if we want to approach damping in a system like this, we'd actually express velocity as something using the backward Euler difference scheme. So basically, velocity is going to be the current value minus the previous value of a position. And so we'd end up with something like in equation 11, where the force applied by a dampened spring would be one term which depends on the difference in positions between the modules it connects, and one term that depends on the difference in relative velocities between these connected masses. And of course, Newton's third law means that an interaction must apply its force symmetrically and with opposite signs to the elements that it attaches together. So the force that this spring is going to send to mass number 1 is going to be minus Fn, for instance, and the force that it's going to send to mass number 2 is going to be plus Fn. And that's basically all we're going to have to work with, is this system where we have masses that evolve over time depending on their state, so their position and previous position, and on input forces that they receive. So they're going to be objects that take a force as an input and output a new position. And on the other hand, interactions are things that will take in two input positions and velocities. So basically the data from two mass elements as an input, and that's going to produce a force that we can loop back into these mass elements. And that's basically all we're going to be working with. It's kind of really simple in a way. So now we have the equations for simple masses and springs and things like that. We can have a look at how we've implemented these and how they work within mi.lib, which is our Faust library. You can find the library in the standard Faust library. So on the Faust library's website, you have this MI section. And here you can have a look at different papers that cover mass interaction physics. And you have the documentation for the library. And what we're going to do is go straight in and have a look at our basic mass. So mi.mass. I'm not going to explain the parameters just yet, but just to show you how it's built within Faust. It's designed as a recursive body abstraction, and this is used with a let-rec function within Faust, which allows us to basically write this equation 3 as is into Faust. So this mass element expects a force as an input and produces a position as an output, and inside it you have basically state variables for position and delayed position. If we now look at spring damper, for instance, mi.spring damper, again I'll just kind of set these to basic values for a start. Okay, so this is a basic linear spring damper. It takes two input values, which are the positions of the elements that it's going to couple together. One part of the system is going to calculate a difference in position between these position values and apply that, multiply it by a coefficient to give the stiffness term. And the other one, using a small memory system, is going to calculate the difference in relative velocities between these two inputs. And the output is going to be the force produced by the spring, and it's going to apply on one hand with a -1 multiplication to account for Newton's third law, and on the second outlet it's just going to pass straight through. So now that we have this, let's try and design our first very basic mass interaction system. So we'll start from the mass again. And so the first parameter, the first argument to the mi.mass function is the discrete time inertia, so this big M. The second is a gravity value. We can just leave that at 0 for now. And then you have the initial position, 0, and the initial delayed position, which infers velocity, which is also 0. It's important to specify here that all the masses in our systems are going to move along a single 1D axis. So we just define positions as scalar values here, which is different to, for instance, 3D mass interaction modeling that we might discuss in perspectives. So we have our mass here, and what we could do just to check if this guy works is set up an input function for it. We could use a button, call it test, send that through ba.impulsify just to make sure we only send one impulse when the button is clicked, and we're going to give this a really tiny value here. So we created this input, and we're going to just put it in as an force input for this mass. So there you have it in the diagram. And if we run this, well, it all kind of happened fast here, but if you manage to see it on the output analyzer, we sent a force impulse to this mass, which isn't attached to anything, that isn't subject to any gravitational pull or anything, and it just basically flew up at constant velocity, which is what you'd expect from a simple physical system like this. If we send a slightly smaller force, it moves up slightly slower, which kind of makes sense. So this isn't really exploitable for anything, especially not sound synthesis. So let's start making something slightly more complex. One thing that I forgot to mention is that all of these examples that I'm going to be covering are placed in a GitHub repository that's going to be given with the workshop. So you can either code them at the same time as I do in real time, but you can also find all these examples with some cleaner comments and things like that on a GitHub repo that will attach to the workshop. And so now we're going to build a basic oscillator. And to do this, an oscillator is going to be a mass, a fixed point, and a spring damper between the two. Well, a damped harmonic oscillator will be. So we'll put an mi.ground. Sorry, my typing is horrible. Mi ground, and this only takes one input position, which is 0. We'll take away this input function for now. We don't really need it. So here we have two material elements in the system and nothing else. And one thing that you need to know with mi.lib and with this mass interaction thing is that in Faust we're going to define all our mass type elements as one parallel composition and all our interaction elements as another parallel composition that follows it. And then we're going to sort out basically routing functions to pass the right positions from the masses to the interactions and the right forces to feed back from the interactions into the masses. So if you just want to put one spring damper, for instance here, spring damper, blah blah blah, give stiffness value here, damping value, and the values here are actually the delayed position of the mass and of the ground module, and these are just needed so that the first step of computation for the spring damper computes correctly. We can, well, don't have to pay too much attention to that right now, but it's quite important to keep in mind. And so there we have a system. So we have material elements going into an interaction, but then we just send the forces out and we don't do anything else. So we don't have a coupled physical system here. And that's what I'm going to do now. Just make this slightly cleaner looking. You're going to see a lot of routing errors and things like that in the first steps of me making these models. And that's just something that happens in Faust. Anyone who tells you that they can write seamless Faust code without generating cryptic errors is either Jan or a liar. So I have my cheat codes here, actually, just to make sure I kind of know where I'm going with these models. So while I was rambling on here, what I did is build this recursive loopback composition thing here. Can't remember the exact name in Faust terminology, but what it does basically is takes the forces that are output by the spring damper and loops them back to the masses. And that is, well, that's a good first step, because that means that we actually have this system which will start behaving like a harmonic oscillator. And if we want to check that, we can just set an initial value for the mass delayed position and report it into the spring damper here. And if we run this, it's kind of faint because I've given a small initial velocity, but we can actually see that something is moving and we can hear this tiny harmonic oscillator sound. So let's take these back off. Problem here is that we have the system, but we don't really know how to we don't have much control over it. We don't really know how to input things into this kind of closed loop system. Don't really know, well, for now we're listening to the force produced by the spring, which is maybe not what we want. And so that's what we're going to do now, is build some stuff around this to make our life easier. And so the first thing that we're going to do is be able to add an input force to the system. And for this, I'm going to use the with system in Faust to write a routing function, root forces, and this is going to be placed just after the spring damper. So the spring damper produces two opposite and equal forces. We're going to call them FSP1 and FSP2. And what we're going to do quite simply is say that this routing function outputs two signals, but in the first one, which is the force that applies to the mass, we're going to say that is FSP1 plus input 1, and the other one stays FSP2. And this is going to be placed right here after the spring damper. Let's have a look at the diagram. So here we have it. We can bring this impulsify value up a bit now, probably. And if we run this, it's still very faint. I'll take it up to 0.5. I hope this isn't too loud. We'll see. Okay, so now we can actually input a force into the oscillator, which is nice. And however, we're still listening to the force generated by the spring damper, so that's not great. And to help us out with this, I'm going to write a root positions function, which is going to go after the masses, and it's going to take position of M1, which is our mass, and position of ground, which is the ground element. And what we're going to output from this is the positions that are needed by the spring damper, so PM1 and PG, and we're also going to add a third signal, which is PM1 again, and that's basically just adding a cable so that the position from this mass can run along through here and go to the output. So we'll set this up here just after the masses, and this is giving us some errors because we're adding, well, we basically have three signals now here running into the spring damper section, and we only have two inputs for the spring damper and for the root force function. So we're just going to add some pass-through signals here. Okay, so now see we have this system which duplicates the mass position as an output, and this runs along to the output here, and what we can do if we just want this position output and that we don't want the force outputs of our spring, which we might not be interested in, we can just discard the first two signals of this guy and add one pass through for the position. Okay, so we've cut these connections here, and if we have a look here, ooh, this is loud, take it down a bit. So we have a harmonic oscillator that we can send an input force to, and we're listening to the position of the oscillator, which is nice. And this is where things get slightly hairier, so bear with me, and we're going to do things the hard way first, and then we'll see how we can do them in a much easier way. So first we've added another mass up here. We've added another spring damper to the system, and obviously none of this compiles anymore because none of the routing is correct anymore. So first thing we're going to do is change the root position function here and add PM2, which is going to be the position of our mass number 2 that's going to be around here. And the two spring dampers that are going to be here are going to expect the positions of the masses that they connect as input. So that's the order in which we need to place things. So our second spring damper is going to act between mass 1 and mass 2, so PM1 and PM2. And we still keep PM1 as a pass-through signal for the output. So in a similar way, we're going to change the forces here, the force routing function. So we're going to do S2, well, FSP2 actually is kind of more correct. Well, no, actually, F2SP1 and F2SP2, because that's the two outputs from the spring. And so this kind of builds, but in a weird way now. But we need to think about what this root force function needs to be doing and how this system acts. So the first spring damper connects the ground to the first mass, and the second one connects the first mass to the second mass. So the forces that need to be sent back to the first mass are the first outlet from the first spring damper, the input force that we added earlier, and the first outlet from the second spring damper. And we also need to add another force outlet, which is going to be the force acting upon the second mass in the system. So that's F2SP2. And so here we can see this horrible sequential composition error in Faust, and that's the stuff that you might have to deal with if you try writing these codes by hand. It kind of gets messy quite fast. And the problem here for this is that we've created a routing function that creates 3 output forces that need to be looped back into the masses, but we haven't changed the value 2 to 3 in here so that this actually works the way it should. So the force that's destined to the first mass is looped back here, then the second, and then the third. And this should build. I think it has built. And oh, this happens sometimes. I just need to reload the page for the audio to come back. There we go. And if we actually listen to this in some more detail, this actually no longer is a simple harmonic oscillator, but it's a system that has 2 modes of vibration because we have 2 masses in the system. However, if I told you now that we were going to use the same principles that we had been using up to now and build a string of 20 masses or something that's not regular, you'd be looking at me like I'm crazy, because this is a pain. Doing this by hand in Faust is tricky because you have to do lots of mapping and things like that. And actually we have quite a nice solution for this, which is a tool called MIMS, which is a mass interaction model scripter. And we're going to go and find this guy. So if we go back to the MI Creative website, here we go. go to something called tool MIMS. We've built several prototype versions of this model scripter over the last couple of years, but the one we're going to use now, and probably the most stable one, is this MIMS Online, which is a JavaScript interface that allows to design physical model code, represent some features of the models, and then convert that automatically into either Faust code or Gen code for MaxMSP. So the first thing we're going to do here, for instance, is build a mass, and there's a help section here that shows you what the different modules are and what the terminology for scripting them is. What we've done here is set up a first mass that's named M. It has an inertia of 1, and this here is the actual position of the mass on this bench. So we have one element here, and that's it. And we're going to redesign the system that we had before. So we're going to put a ground somewhere, place it somewhere different, just so there we go, so we can see both of them. Going to put a spring damper between these. So the way you do this is you declare the name for the spring damper, the type. Of course, you can look at this again in the help section. Then we define who's going to be connected by this guy. So M and G, and give it a stiffness and a damping value. And here we have this line here between the two. And now we're going to set up an input being a force input on M, and out1 is going to be a position output also on M. Sorry, I forgot T here. There we go. So we have these kind of funky input-output representations here. They might change over time, but I mean they help us see what's going on at least. And the cool thing here is that this generates this Faust code automatically, which is nice. And so if we take this, bring it back into the Faust IDE, we're going to scale down this force input just a tad. There, so we've rebuilt the basic oscillator. And if we want to find the system that we had before, the two masses and fixed point system, we just set up a third mass here. So this compiles, and we can see the third mass, but it's still not attached to anything. And going to add a second spring damper between M and M2, same parameters for now. And there we have it, and we can take this guy, go back into the IDE, copy all of that. Sorry, that was loud. One thing that you have to do once you have the scripted model code generated is often scale your inputs and outputs a bit, just to make sure that the excitation you give to the model and what comes out of it is kind of on a normal scale and doesn't saturate the audio output. And that's basically it for our first model, and maybe we can start building some extra things now. The first thing I'm going to show you is how we can excite this model slightly differently than we had up till now. And we're going to do that first by removing this force input, and we're going to add a mass to the system. We're going to call this mass hammer. It's going to be a regular mass. We're going to make it a bit heavier than the others, and we're going to set a parameter that we're going to call gravity. And this is something that is important to know, is that you can say grav here is a parameter and has a certain value, so I'll put it as 0.5 for now. So that's the gravity that applies to our mass, and we're going to define its initial position here. So let's just put it at 1, 0, and 10. So we're going to place it above the other masses in the system, and we still need to give it an initial velocity. So there we go. now we have this mass here, and we can see it. And what I'd like to do is basically throw this mass down onto the this 2-mass system, and so I'm going to give it an initial speed of minus 100 units per second, and that's this last parameter here that you can find in the help file. And if I want an interaction between this and what's underneath it, I'm going to add another interaction, which is a contact type interaction. It's going to act on M2, for instance, and well, M2 is going to be collided into by the hammer. So there we go. These contact interactions take a stiffness term and a damping term. So let's just set it up like this for now. Now we can see this in the scripting window, and we have generated code for the model. Let's bring this back into the IDE. And I'm going to bring up the audio gain slightly so we can hear this better, but you might have heard it already. We have this kind of bouncing ball that bounces on this 2-mass system. So now what we're going to do is design some strings and things like that using this mass interaction model scripter. So we're going to take all this down, and we actually have a script generator, which is quite practical, in which we can ask to define a string with a certain number of masses with a given name, initial parameters, so you can kind of look into all that and see what it does. And if we just slide this guy into here, we have a string of 30 masses. And so first things first, I'm just going to make sure that we can interact with this string. So I'm going to add a force input on, I don't know, mass number 10 of the string. You can see it appear here on the render, and we're gonna get an output position, pos output, and that's gonna be on the mass number, I don't know, 27. And he's not happy with that because I had a typo. So this again generates some Faust code, and you can see here that the routing functions would be extremely annoying to code by hand, and so we're kind of happy that this all is done for us. So here we have it. I'm just going to reduce the force input signal to make sure that this isn't too loud. How does it sound? Sounds nice, sounds low, so we can bring up the stiffness of the string here. Interesting thing when you generate with scripts is that it automatically creates these labeled parameters so that you can change these directly in Faust. So if we take this up to 0.3 maybe, there, and now we can, there. So this is kind of a reasonable sounding, very basic string made of 30 masses. So if I want to pluck this string, I'm going to take out the first force input, because we don't need that anymore. And I'm going to change this into a position input, and it's going to have an initial position of, let's say, 1, 1, 0. And what that does, if we look at the model view here, you can see a mass here that's been added to the system, and that's actually going to be controlled by an input signal in Faust. So it could be a slider, it can be audio, it can be basically anything that you want. And quite simply, we're going to add an interaction called an NL pluck. If you look into the help, you can see the parameters that it expects, and we can show you the force profile as well for the interaction. And this is going to act between the input 1 and between I don't know, mass 18 of the string. First parameter is the plucking stiffness. I'm going to set this to 1. The plucking scale basically dictates where the tipping point for the plucking interaction is, so where the pluck kind of goes through the string and allows it to vibrate freely. And the last parameter is optional, but it's damping, and so that means that when you rest the pluck against the string, it's actually going to dampen the vibrations and not just kind of create this weird inharmonic tone. So I think this is okay. So let's go back into the IDE. we're here, and see we've changed this now. This input is now a position input, and it has a slider, and it works. We'll bring the audio up a tad. So here we're in contact with the string. We're pushing it up, and at one point we pluck it. So the pluck goes through the string. So quite simple, really. And let's say we want to make things slightly more complex. Let's add a second position input. Put this one at 210. The only position that really matters here is the Z, because that's the initial height of the pluck. All the rest is just for the model rendering, so it's just for us to kind of see where things are and how they're working together. And we're going to put C, a contact between a certain point of the string, strm. We have a 30 mass string, so I'm going to go ahead and put on the damper on 20, so we can maybe excite a natural harmonic. And so a contact interaction between that part of the string and the input, and we're going to make it quite soft in terms of stiffness and quite damped. And what that means, you can see it here, is that we're going to add this damper, so we can come and press down onto the string and change its vibrating properties, because we're basically applying pressure onto it. So if everything goes well, now we have two inputs and outputs. Actually, one thing that might be nice to look at is what the model looks like for something like this. So you can see we have all the array of these masses, which are actually oscillators in this case, the fixed points, the position inputs, the master link routing, all the interactions, and the routing here, and it kind of all goes back. So that's kind of simple enough for a 30 mass string, but it becomes absolute horrible stuff when you have bigger models. So now we have two position inputs. I'll just up the output gain a tad. Okay, this is okay. And if we bring this guy down, we can actually, we're just pressing lightly on the string, and we can bring out some natural harmonics. This the mass isn't positioned exactly on a vibration node of the string, so we're actually kind of damping it quite a bit, but it still works. And now, finally, let's see if we can bow the string instead of plucking it. So we're going to use exactly the same system as we had before, but we're going to change this NL pluck interaction to an NL bow. NLB we're going to call it, still between the first input and an element of the string. And the parameters for bowing, you can find them in the help here, are the nonlinear friction and a scaling parameter as well, and you can decide if you want a smooth function or a linear function, or a piecewise linear function for the bowing interaction with the last term. So what I'm going to do to make things easier is I'm going to create parameters for the nonlinear friction value and the nonlinear scale value. So I kind of know in advance which parameters I need here in terms of values, but you often need to explore a bit to get the right values that give adequate friction for a given system. So the things kind of look the same now, except if we go into here, we can see that we have an NL bow here in the system, and we have some additional parameters for the friction. So let's bring that back into the IDE. It's going to look more or less the same as it did before. And now what we want to do, well, we can see if this actually does anything yet. It does, but it's very, very low, and that is because I'm going to have to scale some of my data here. The bow position, which is the first input, is going to have to move in a lot broader ranges for this to actually generate enough friction. So with this set of parameters, if I give it a course between minus 300 and 300, that's a decent value. So this works, but it's pretty ugly, and the reason for that is actually quite simple, is that bowing input signals need to be very, very smooth in order to perform well with, well, basically these velocity driven friction algorithms are very sensitive to noise in the input value. So I've just set a bunch of smooths sequentially after each other here in the position. And there we go. And we still have the finger to generate harmonics. So we can slightly change the way the bow sounds if we press down on there. And of course, what we can do is create a new slider here. So the NLZ actually corresponds to bow pressure. And we're going to set this guy initial value at 0.3, going from 0 to 1 with a scale of 0.001. And so now we still have the bow, and we can lighten the pressure. So nice and smooth bowing. Or we can up it like crazy. And start getting some nice screechy sounds. And finally, what I'm going to show you now is how we can make stuff like this sound a bit better. And that basically pertains to the complexity of the vibrating structure. We had a very basic 30 mass string here. And 30 masses, in all honesty, isn't enough for a discretized mass interaction string to sound kind of very convincing and real in many cases. So I'm just going to go ahead and set a string with 200 masses. I'm going to bring this in here. So the script is getting a bit longer, but it doesn't really matter. And if we look at the model view, it still looks the same, but it's kind of more compacted. And now what we might want to do is just change these contact positions slightly. So this guy is going to dampen the string at half the length at 100. The bowing position is okay, we'll keep it there. And we'll set the output position slightly closer to the edge actually, so on the 10th mass. Note that you can also use several position outputs to have stereo or as many channels as you want. That's not something that we've done, but you can. And so we're going to take this guy, go back into Faust. I'd like to keep my position scaling for the bow, so I'm going to take all this stuff here and delete it. And probably have some duplicated stuff here that I need to take off, but there, so we've kept the bow, and I'm just going to, just going to put the bow pressure function back in here. So 0.3 from 0 to 1 by steps of 0.1, that should be okay. So same object, but and what's happened here? We probably need to lower the output gain first. Oh no, I know the problem. We've made this string very floppy. I forgot to set the initial stiffness, so it's super floppy, and that's why it was all over the place. So if this is better, and if we bring this there, and if we're good enough, we can get some kind of decent Helmholtz motion going. So these triangular waves you see on the output, and if we press down on this harmonic point, we'll tend to bring out the first harmonic of the string. So now that we've done some basic strings and things like that with MIMS, I'm going to show you a slightly more complex model that I designed earlier. And this model contains several triangular structures that we're going to be able to hit with mallets, basically. So I'm just going to slide this MDL file into the editor and press Control Enter to make sure it recompiles the view. And here you can see what the model looks like. So three triangular structures that have fixed points on the extremities, and you can see the code generated here for each of them. And at the top of the model we have all the kind of coupling and interaction elements for this model. First of all, we have a common bridge, which is placed here, and that's a big large mass which is going to act as a kind of coupling point for the sound. So we're going to connect each of the triangle structures to this bridge, following well, these spring connections here. And then we also have hammers. We have 3 of them up here that you can see probably in the interface. And these are simple oscillators that are resting above these triangle structures, and we're going to be able to send force impulses to these hammers so that they come down, hit the triangles, and come back up. And the damping of the oscillator is placed near critical damping so that you don't get multiple rebounds and things like that. And finally, the last thing that we have is some small non-linear spring dampers here, which are placed between the different triangle structures. And what that does is just adds some more sympathetic resonances between the structures, and the non-linearities in these spring dampers bring out some interesting sound aspects. So let's go ahead and grab the Faust code for this, go back into the IDE. It's quite a big model, so it will probably take a few seconds for it to compile. Let's see. Yeah, it's okay. We're not too bad. And what I want to do now is just to condition my my input signals and things like that properly, so that things work the way we'd want them to. First of all, the force impulses that I'm sending to the hammers need to be directed downwards, and I'd like to be able to determine the amount of force that I send to them. So I'm going to add another slider that's going to be called intensity, and that's going to go from 0 to well, it's going to start at 1 and go from 0 to I don't know, 4 by steps 0.01, and this is going to be common for all of my hammer inputs. So I'm just going to put this here and here. So this is going to control for all of them. If I start using them here, we can't hear anything because the this huge bridge that I connected between all these triangles only basically its impedance is so massive, its mechanical impedance, that its motion is very small. So I'm going to multiply the output gain by 100, and I could actually push it probably even to 1,000 to okay, so here we're starting to get somewhere. I'll bring it up slightly more still. And what I'm going to do is add some controls for the stiffness of each of the triangles. So call this one triangle 1 stiff, go from 0.001 to 0.3 by steps 0.01, and I'm just going to copy this and duplicate the control for the other triangles, and then we'll see how this model actually sounds. So there we go, we have everything here. If we start using the hammers, we have quite a moderate attack here, and if we bring the intensity up, slight saturation on the audio here, that's I should bring the gain down maybe a bit. I'm going to up the damping slightly because the resonances are very long here. And if we start detuning these triangles from each other, we can get some interesting sonic results. So this is kind of moderate attack levels, and it and if, on the other hand, we bring the intensity down to something really small, we get this nice, very soft attack. Now I'd like to discuss some perspectives and also some limitations to the work that we've done regarding mi.lib. And the first of these concerns optimization of the actual simulation code. Despite the system allowing to easily model fairly complex systems and such, we still see quite an important gap in performance from automatically generated Faust C++ code to manually handwritten and hand-optimized C or C++. We're yet to conduct extensive benchmarks on this, but the performance gain of writing straight C or C++ code for a given model can be anything from 3 to even 10 or maybe 20 if you start using manual vectorization schemes and things like that. The second aspect that we haven't implemented yet in our library is the use of macro physical elements in the same way you do in finite difference schemes. Each physical construction that we build in mi.lib so far is built by assembling single masses and interactions together, often in quite regular and homogeneous patterns. And if we actually create macro elements like a string, a mesh, a triangle, or anything like that, on the one hand, we can optimize the formulation of these elements to speed up the calculation. And on the other hand, it opens up possibilities for interpolation in connection points or coupling points to these structures, for instance, which is something that we cannot do as of yet with the core of our library. There is one example code in which I've prototyped some of this that I'll join in the GitHub repo, so you can have a look at what we can do to build kind of wrappers around these macro objects like strings, but there's still a fair bit of work for us to be able to integrate that fully into the library.
Thanks, James, for this wonderful presentation. That was actually really, really great. We do have 5 minutes for questions. So I'm not sure if people actually asked a lot of questions on the chat. I see a lot of things are actually going on right now, but do you want to say anything, James?
Yeah, one thing I can say is that for the history of mass interaction physics and all that, I mean, there's a super long history of these stuff dating back to Acroy and to a bunch of other things. I mean, Edgar Berdal implemented some mass interaction stuff in Faust a few years back as well. So there are a bunch of papers and tools that you can get your hands on to kind of figure out all the different flavors of this stuff. And yeah, one thing I might discuss a bit is what I introduced in the perspectives in terms of where we're kind of trying to go from here and what limits we've found. Definitely, I hope we can address the kind of bottleneck in computing performance that we get through this automatically generated Faust code, compared, for instance, to handwritten C++ code. And I know that's something that we've discussed with you and Jan quite a bit, but I think there's still room for improvement there. And I think that one of the really interesting perspectives, and that's going to be, well, that you'll see a lot more of in Ricardo's presentation actually, is to offer basically full kind of coupling in compatibility of models that include punctual mass interaction elements and more finite difference expressions of virtual acoustical structures. You saw here like the plates and the strings that we made were all just like basic elements connected together. And yeah, making basically when you make these structures and you know their topology in advance, for example, a string or a mesh or something like that, you can do all the cool stuff that you do in finite difference schemes, like interpolate coupling points and things like that. And that's something that works in MIGen, which is basically the kind of variant of this stuff that we've done for Max MSP. And it just turns out that writing this kind of stuff for a functional programming language such as Faust is a bit more of a challenge. So we're kind of working on it, and I think we'll get there fairly soon. And yeah, there are a few other questions, maybe. Yeah, FG asked something about performance between Faust and Gen. They're sensibly the same, actually. The generated code, the C++ that Gen gives us is about the same as Faust in terms of performance. And have you thought about writing a custom C++ converter to improve performances? Yeah, that's something that we actually do for kind of one-off models that we design when performance is really an important aspect for larger models, for instance. But kind of taking that into account and making something that is both fully modular to allow you to construct any kind of physical mass interaction network, and that on the other hand is extremely optimized for real-time performance, is always kind of a challenge. Like if you write a model in C++ using manual vectorization to make sure that everything is sped up to the max, that kind of doesn't always play well with being able to just kind of, you know, drop a model file into something and have that run very efficiently. Yeah, I think that's pretty much that for me.
Great. Well, thank you very much, James. I think we're ready to switch to the next presentation. And I'm sorry, everyone. This is kind of a very dense day with a lot of information and a lot of very technical topics. You know, like, but I think that's the point. But thanks again, James. Thanks.
Cheers. No problem.
And, the next presentation will be by Ricardo Russo about the new finite difference scheme library in Faust.
Hi everyone, I'm Riccardo Russo, a master student at the Aalborg University in Copenhagen, and this presentation will be on building finite difference schemes physical models in Faust. To do that, we will be using the FDS library, which is the result of a work I've done at Grumman in the previous months, with the goal of introducing finite difference scheme synthesis into the Faust programming language. This is the agenda for today. This workshop will be divided into two main parts. In the first part, I will introduce some of the FDS theory. Some of you may be already familiar with this, for others it will be completely new. This part is mainly oriented towards those who are new to FDS, and is intended to give you some of the basis of the mathematical basis that will be useful throughout this tutorial. Then I will move to the hands-on section. First, we will implement the first FDS model without using the library. This to understand the basic principles of finite difference schemes in Faust. Then we will have a brief look to the cellular automata approach, which is used inside the library, and later we will build all the schemes we obtained on paper in the first part by using the library. Lastly, we will take a brief look at the interaction models. So first, what is a finite difference scheme? It's a discrete model that simulates a continuous system. It's a method which is largely used in engineering for system simulation, and it's actually a pretty old idea. Basically, it consists in numerically approximating a continuous system, usually a system of partial differential equations, with a discrete space-time grid, like the one that we can see here in this image, where we discretized the time and space axis, obtaining a series of discrete points. So why FDS? What are the advantages and disadvantages with respect to other physical modeling techniques? Well, directly simulating a mathematical model allows to not make any assumptions on the mathematical solution. So this makes this method very generalizable and flexible, and also very accurate. So, for example, it's easily applicable to nonlinear systems. On the other hand, though, it's really computationally expensive. At the moment, the guys from the Stefan Milblau group are working on state-of-the-art physical models, which can produce realistic sounds, but also which require less and less computational power. Here are a couple of examples. This was a trombone, and here's So, as you can see, this method allows to model all the tiny details that make a sound realistic. So, first, let's start from the basis. The starting point for finding different schemes is that musical acoustic systems are defined by partial differential equations, PDEs, which are accompanied by regions of definition, boundary conditions, and forcing terms. The state of this system depends on the time instant and the spatial coordinates. It can be defined as a function u, which depends on x and t. So the first steps for defining a finding difference scheme physical model are first to formulate a mathematical model. Then we need to define the space and time sampling steps. And once we obtain those, we can discretize the partial differential operators to obtain an update equation. Lastly, we need to implement the boundary conditions. So first, let me do a parenthesis on the notation that we will be using. This is the same as it's used by Stefan Milbau in his book Numerical Sound Synthesis. And it's basically just a way for writing partial derivatives. So here, instead of having this expanded notation, which is most commonly used, we can just write it with a subscript variable, which indicates the variable in which we're going to derive. And this is, for example, first order, second order, and mixed derivative. This is just a notation, basically. So let's get into the real stuff and build our first finding difference scheme mathematical model. So the first thing we need to do is to define the mathematical model. And the simplest possible equation in acoustics is the 1D wave equation. This is a second order partial differential equation in time and space with solution u, which depends on time and space. A partial differential equation, well, a differential equation is basically an equation in which the unknown is not a variable, but it's a function. And so in this case, our function is this u. And u represents the state of the system at time t and position x. And the state is, for example, the vertical displacement of a vibrating string, or the pressure value inside the tube, or things like this. C is the speed of sound in the medium, and the medium is the material of which the system is made. So, for example, for a string is metal, for a tube it's air. T is defined over a positive real domain, because of course time can't be negative. And x is usually bounded over a finite length L, which is the length of the string, the length of the tube, or in general of our object. And we can calculate the fundamental frequency of vibration using this relation here. So we have our mathematical model, and we said that the second step is to obtain the sampling grid. And to do that, we need to first define two sampling steps, k and h, for time and space. These are just two numbers that define the space between the sampling points. So then we can move on the grid with the two integer indexes n and l. And so what we obtain once we discretize our system and we simulate it, what we obtain is a discrete u of ln, which approximates the continuous solution to the system that we saw before. And this discrete function will be made of n equals L over H data points, because of course the number of points will depend on the sampling grid. So if our L is 1 meter, for example, a 1 meter long string, then we will obtain a number of points which depends on 1 meter over the sampling step. So we need to be aware that the two sampling steps are not independent, and they're actually bounded by a stability condition. In general, finite difference schemes physical models are tend to be unstable, and when they are unstable, they blow up. So the signal goes to infinity, and what you hear is just a really weird noise from your headphones. So to be sure that our system will be stable, we need to impose this condition, and so we cannot choose these two steps independently. And this is the Courant-Friedrichs-Levy condition, CFL. So we have our mathematical model, we have defined our sampling steps, and now we can go on and discretize the partial differential operators, which is actually the core of finite difference schemes. Here we have the difference operators in time and space in different versions, and what you need to know is that the centered one is more accurate. This looks like a lot of math, I know, but actually these are just basic algebraic operations. These can then be combined to obtain higher order derivatives. Okay, so we have everything we need, and then we can now discretize the mathematical model. So we started with this equation, which is in the continuous. Then we can apply difference operators. I will try to show most of the steps to make it more clear for you. So we can then expand these as we saw in the previous slide, and this is what we obtain. Then we need to solve for u of n plus 1, which is our unknown, because of course it's the next step for every single data point, and it's what we are looking for. So if we solve for these, this is what we obtain, which is an explicit recursion relation that can be directly solved numerically. So here you can see a graphical example of the time and space dependency for the relation we obtained in the last slide. Basically, to get the state of our unknown, ul of n plus 1, what we need is the current state of the point L, the current state of the two neighbors, L minus 1 and L plus 1, and the past state of L. So you might have asked yourself, how do I know the current and previous steps? How do I get them? Well, we decide them. So this is called setting the initial conditions, and well, to make things more simple, we can set everything at 0. So what we do is, when we start the simulations, we first set all the data points for the current and previous time steps to 0. So we have our initial starting states. And also, what do we do at boundaries? When we get to the boundary of to the endpoints, for example, of our string, we would need the next point to calculate the next state of this point, but we don't have them. And there are many things we can do. This is called setting the boundary conditions. The most simple and used boundary conditions are these two, the Dirichlet and Neumann conditions. In the Dirichlet condition, what we do is simply we consider the next point, the virtual point, to be 0. This is, for example, the case of a string, where the next point, well, the two endpoints are fixed and they can't move. The Neumann condition, on the other hand, involves solving a little derivative like this. And it can be considered as a free end. So we have our point that it's free to move. For example, it's free at string, which is free to move on one side. In the case of a tube, things are the other way around. It's pretty weird, but it's you can consider that if cube has an open end, the pressure in that point is 0. So because it's the pressure of the atmospheric pressure. So you can see it this way. So now let's go on and try to implement a Neumann condition in the point L equals 0. We need to solve this little derivative, and if we do that, expanding this operator, this is what we obtain. So then we can apply this to the update equation that we had before, and this is what we obtain. So this is the update equation to be used only when we want to calculate the next state of the point L equals 0. Okay, so we did it. We got the algorithm for our first finite difference schemes physical model. As you will see though, the sound is pretty boring, and especially in Faust, since it's real time, it will ring forever. We can fix this by adding a damping term. Every instrument in the real world experiences damping, which is the cause of the outcoming sound to fade out. And we can describe this in math with a term which depends on the velocity, or the first derivative. And here sigma 0 is called the damping coefficient. It's a number which depends on the physical characteristics of the object. We can go on and discretize the damped wave equation as we did before for the 1D wave equation. We apply the operators, the difference operators, and we can then expand them. Now we will skip some math here, but you're very welcome to try and see if you obtain the same result. This is what we obtain, and this is the update relation for the damped wave equation. This update equation has the same space-time dependency and stability condition of the one we saw before, but as we will see, it sounds a bit better. So, before moving to the hands-on section of this tutorial, I would like to introduce you a bit to how these algorithms are usually implemented. In imperative programming languages, we can use arrays. So we allocate 3 arrays for the states, for the time states n-1 and n+1, each one with a number of data points equal to the total number of spatial grid points given by L over H. So we have, for example, our 1 meter long string, and we will have a number of data points, which of course depends on the spatial sampling step H. Then we allocate 3 arrays, each one with that number of data points, and we cycle between them, updating the states at audio rate. We can then obtain sound by reading the current state of a single data point in one of the arrays. So this code snippet shows how the 1D wave equation is usually calculated in MATLAB. The first cycle, this one, is on the time samples, like an audio process callback, for example. And this cycle is the loops between all the spatial points. So this is exactly the update equation we obtained before. And we cycle over all the L data points with to a maximum of n, which is the maximum number of spatial data points. Then we read the samples at out position, which is one of the data points. And then we update the states. In Faust, we don't have arrays, so we have to find a completely different way of doing this, as we will see in the next section of this tutorial. Okay, so now it's time to get our hands dirty and implement all the algorithms that we obtained on paper in the last part of the tutorial. I will try to do everything with the online compiler, which you can reach at this address, faustide.gram.fr, so everyone can follow with any operating system. So the first thing we need to do is we need to understand how to build a finite difference scheme in Faust without using arrays. So let's start with the simplest one, the 1D wave equation, and just to be so we are on the same page, this is what I'm talking about. This was the first scheme we obtained in the last part of the tutorial, and it's the simplest equation, the simplest possible equation in acoustics. So I'm gonna write the equation here so you can see it. So this is the equation that we want to calculate. So the first thing we want to do is we want to set our sampling steps. In audio, what we do is to set the time step first, contrary to what is done usually in other engineering applications, as this depends on the system sampling rate. So we can now set k equals 1 over ma.sr. Here I'm using the ma.sr function, which returns the system sampling rate. Now, we saw that we can't choose the two steps independently, but we have to, we have that, let me write this, lambda needs to be minor or equal to 1. So, this also means that h needs to be greater or equal to c times k. So first, what we have to do is we need to set the speed of sound in the medium, and we will set it as 344 meters per second. And this is just the speed of sound in the air. So now we are ready to set the space sampling step. We will set lambda equals 1, as this is the most stable condition that we can have. So we are as near as possible to the stability condition. So we can say that h equals c times k. And then let me write this for simplicity. We have that lambda equals c times k over h. Okay, so now we want to actually code the update equation. What we can do is to start by coding a function which does the calculations we want. So it takes the present state of itself and the neighbors, which we will call west and east instead of these, which is a bit more complicated to write. And the past state of itself and outputs the next state. So to do this, we can write update eq. We'll take in input u west, u, and u east. So current state and two neighbors equals, and this will actually do this. Let me just copy paste for simplicity. So 2 times 1 minus lambda squared times u minus u delayed. This is the delay operator in Faust. Basically, this means one sample delay. Then plus lambda squared times u west plus u east. Okay, this can work, and this will calculate our update equation. However, if we want to get sound, we need to interact with our scheme, our mesh. So let's add a forcing term to do this. We can add f in, and we will have to also get this from outside the equation. So I'm gonna put this first. Okay, great. So we have our equation that will calculate the state, but as you might remember, this is valid only for one data point. So what we can do is we can place many of these functions in parallel with the Faust par iteration, obtaining our mesh structure, our scheme structure. So first, let's define the number of points that we will want. Let's choose something simple. So now we can define our structure. So as I said, we can use the par operation. Let's build a function called build1d scheme. This will depend on the number of points. This equals to par e points and update queue. And we can already try to run this to see what we get. So let's write process equals build1d scheme and points. Let's try. And this is what we obtain. As you can see, we placed 3 of these blocks here in parallel. And what these represent, you can see this as 3 elements inside an array. So each element in the array will perform the update equation operation. But of course, this will not work at all because we need to fill the neighbor points. And when I say neighbor points, what I mean is that this point here, for example, will take the forcing component, the west neighbor state itself, and the east neighbor state. So he will need a term from the outside, the forcing term from the outside, but also the states from this point and this point. So to get these states, we can create a feedback loop. Let me call a function called, let me create a function called model. This will also take in input the number of points. And then we can call build1d scheme points, then here and bus points, and then we call process equals to model and points. So here what we did is we declared a feedback loop using the tilde operator, and bus is simply a way to call number of signals in parallel. So here we are requiring that what comes out from this goes in a feedback loop inside a bus with 3 signals. So let's try and run this. And okay, so this is what we get. And as you can see, this is more clear now. We created a feedback loop with so since we have 3 points, he created 3 feedback loops with this bus function. Now, the problem, as you can see, is that we need to bring the signals into their correct places. Now they're just going into the first empty spots they find. And to do this, we can use the root primitive. This function works by taking the signals and defining routing with numbers. We will have 3 state signal inputs and 3 force inputs, so 6 inputs. In output, we will have 3 states plus 1 force for each equation block. So 4 times 3 equals 12. Let me let me delete this process because we won't need it anymore. So as I was saying, we have let me call a function called routing points equals root. So in the root primitive, we first need to define the number of inputs and the number of outputs. So I said it's 6, which again it's 3 state signals signal inputs, one for each point, and 3 force inputs, one for each point. And then we will have in output 3 states plus 1 force signal for each equation block, so it's 12. So now things are going to get a little bit complicated, so let me write everything and then I will explain later. Okay, so I created my routing, and what I did is I modified the this version here, which I had before, which I'm gonna delete, and I added before our scheme, I added my routing. So this is gonna take the signals that are fed back from this bus, and this function is gonna take care to route each signal where it has to go. So let me delete this line here, and then let me call the process model and points. Let's run this, and again, this is what we obtain. So this is what the routing does. So if you look at these numbers, what I did was this. So I took the first signal in input, so 1, and routed it to the third output here, 1, 2, 3, because the root primitive is 1 indexed, and we'll see why. And then also the first input, I routed it to the 6th output, 1, 2, 3, 4, 5, 6, and the same for each other signal. So I took the second input and routed to the 4th, the 7th, and 10th output, and these for each signal. Then I took these, which are the 4th, the 5th, and the 6th input, and routed. These are the forcing signals, and routed to the first input for each equation block. As you can see, here there are here we have 2 connections where there is a 0. Root is 1 indexed before, because if I place a 0, this means send a 0 signal, so a null signal, and this is what I do at the boundaries. So here and here, what I'm doing is I'm implementing a Dirichlet boundary condition. So I'm assuming that the neighbor that should be here and here is fixed. So it always sends a 0 position signal. Okay, so we have our working model, but however, we cannot get any sound from it because we need something to interact with our mesh. First, well, as a force model, we can simply, for now, create a button, which I'll call play equals button, and we will send these through an impulsify function, which will turn the button signal to an impulse. Then we need to choose which point we want to send the force to. Of course, we can excite each point at the same time, but it's not really realistic, right? It's like I have a string and I pluck it in every single point at the same time. It's not really physical. So yeah, let's create. Let's start by creating 2 sliders. And then we want to code some functions to send this signal to the right, into the right place. So point selector in will get the number of points and the point we want, and we can use the select out n function, and this will get the same inputs. And also we want point selector out, same inputs, and we can use the select n. So this function takes one input and outputs n, outputs n signals where each one is 0 except the one selected on I. So this is perfect for the input signal, whereas the select n function takes this number of signals, and what it does is it outputs only one of the signals it gets in input. And sorry, I made a mistake here. This is points, because this is the number of points, this is the point we want. Okay, so now let's try this out. We can call our process. Now we have the force signal, and we route that into the point selector in function, which we will take and then this will go will be plugged into our model function, which is this one, and takes n points, and then this will go through point selector out, n points, out point. Okay, so let's try this out. And well, of course, now he's complaining because I have another process defined here. Let me take this out and rerun this. Okay, so it works. And well, as you can see, this was pretty annoying, and the problem is that the number of points is so tiny that the outcoming sound is super high. But yeah, we achieved it. We built our first finite difference scheme in Faust. However, well, if you think about it, it was a huge pain. And if any of you had any experience in coding finite difference schemes in MATLAB, for example, in this moment you might be thinking, okay, but in MATLAB this is way more easy, way easier. And you're right. You're actually right. So we can, let's say, we can use a different approach. If you look at the update equation, you will see that this is linear. So what we're doing is we're simply applying some coefficients to each neighbor signal. So this is the first coefficient, and it's applied to the current state of the point. -1 is applied to the past state, and lambda squared is applied to the two neighbor signals. So, and let me show you something here. Since the derivatives are mirrored, we can define a neighborhood with a radius. So, basically, for example, in this case, we could define our neighborhood radius as 1, because we need 1 point on the left and 1 point on the right. Also, we need to define a time coefficient which indicates how many times back on time we want to go. And in this case, it would be 1 again, because we just want n-1. And this approach is similar to what is done in a family of algorithms, actually, called cellular automata. And this is exactly the approach which is used inside the FDS library. So let's try and build the same, well, almost the same algorithm, but by using the library. Now, instead of writing a function to perform the equation as we did before, I will go on and just define the coefficients that are going to be applied to each of the various states. So we have, let's say, A equals 2 times 1 minus lambda squared. We have B equals lambda squared, and C equals -1. And these are exactly the coefficients that we can see here. This is pretty clear, I hope. Then we want to define the neighborhood radius and the time coefficients. The time coefficient. So we said that they are going to be R equals 1 and T equals 1. So what we want to do now is to create a coefficient matrix. So we want to arrange the coefficients so that they make sense for the algorithm. So A will be applied to the current state of the point, B to its neighbors, and C to the past states. So for the time instant n, we can call mid-coef equals B A B, and for time instant n-1, we only have the current point, so L n-1. We don't have, for example, L plus 1 n-1 or L minus 1 n-1. So we can apply 0 where we don't want to get the signal. So mid-coef del equals 0, C 0. No, sorry, 0. I hope this makes sense. If I go back on the scheme, what I'm doing here, this would be mid-coef. So this part here is A, this here is B, and it's gonna go to the neighbors, and this one is C, and we don't want the neighbors past signals, so here's why there is a 0 here. So we already implemented the 1D wave equation, so let's make things a bit more complicated and let's implement different boundary conditions for the left point. So what we want is to implement the Neumann condition, which is this one, the one we saw before. And let me write the equation for the Neumann condition. So now we want to define another coefficient, which is going to be D equals 2 times lambda squared, and the corresponding matrix, which is going to be left coef equals 0 A D. This is the left boundary, so we physically don't have another point to get the signal from. So well, the coefficient is gonna just be 0. A, it's the same as you can see here, and here we have D, which is 2 times lambda squared. And for the past state, we still have C, so we don't have to define anything else. So now we want to decide what the coefficient scheme will be. So we want to set the coefficients for each point in the mesh. So first we want to set number of points again, and it's gonna still be 3. Then defining the scheme is very simple. We can simply use a par iteration, since each point will have the same coefficients matrices except for the for the left one. And we will put the left one first because, well, it's left. So let's call our scheme equals left coef mid coef del, again because for the delayed version we don't have another coefficient for the left point, and then we can use the par iteration. So it's gonna be e minus 1. It's gonna be points minus 1 because, well, we already defined 1 point, the coefficients for 1 point. And then mid coef del. Okay, so now the hard part is done, and we can now simply call one library function from the FDS library to obtain our working model. So let's call process equals fd.model1d, because we are in one dimension, and points. This will take in input the number of points, the radius, the time coefficient, and the scheme. So points, and well, let's try and run this. And as you can see, it is a bit different, but this is exactly the same model that we obtained before, except, and if you check here, this is the same routing that we had in the previous model, except that now each point takes in input also the scheme coefficients. As before, if we want to interact with the mesh, we need to put some other functions. And now, however, we might want also to get the signal or to excite our mesh in between 2 points. And to do that, we can use the interpolation functions that you can find inside the library. So instead of getting these, we can try and do something else. So we can call our new process function play. This time I'm gonna need to spread this signal, and then we can call fd.interp1d and points. And this takes, as before, it takes in input the number of points and the point that we want. Then we can call fd.1d and yeah, again takes number of points, r, t, and the scheme. Well, then we can call also fd.interp1d out, which is just the it's the version of this function just to get one signal, basically. So and points out point, and let's try and run this. Okay, so this works, and it's just as annoying as it was before. But I hope you agree that this was easier than the approach we used before. Now the cool thing is that while before we had to change the routing for example, if we wanted to change the number of points or change the type of a scheme, we had to rewrite the routing each time manually, and that's very annoying. But in this case, we can simply, for example, change the number of points. And also, yes, another thing, since we are linearly interpolating, we can change the step to be a float, and so we can get the signal in between 2 points. And also, let's make this stereo. Okay, so let's run this. This takes a bit more. Okay, as you can see, things are starting to get a bit more interesting. But we don't have dumping yet, so this is still ringing forever. So let's add some dumping to obtain something more interesting. So the first thing we notice is that we have another parameter, which is dumping coefficient. We can now simply take this value, 0 equals 500. Well, now we have to redefine our coefficients. So first, let's set the neighborhood radius, which is still 1, and time coefficient, which is still 1. But then, for our points, we will have a equals this. And then we'll have b equals lambda squared over c1, which is this. And then c will be c2 over c1, which is this. And then let's define what these two things are. C1 equals then C2 is going to be the same with the sign inversion. As before, we can write mid coef equals B A B, and mid coef del equals 0 C 0. We're not gonna implement any other boundary conditions. We can simply call our scheme function, well, declare. Now we can simply, we will simply have a par iteration, par points min coef del. We can keep this structure as before, and let's try and run this. Yeah, of course he is complaining because here I miswrote this. Let's run this. And okay, here we have it. Let's try. This starts to be a bit more interesting. At least it sounds more like a string. We can decide where to excite it. And so, as you can see, by using the library, it's way easier to write fine difference schemes in Faust. Before concluding this tutorial, I would like to briefly show you something more advanced. So until now, to excite our model, we used an impulse directly sent through the mesh. And here I'm still on the damped wave equation code with only 5 points. Now, in reality, things are of course more complicated, and interaction is usually nonlinear, and it depends on the current state of the mesh or of the model. This is called coupling, and now I'm going to show you how to implement this in Faust with an example. I had to reduce the zoom because of a GUI problem, but you can go to examples, physical modeling, FDS, piano hammer string. Okay, so let me reduce the number of points for more clarity. I'm gonna run. And this is our new process diagram. So as you can see, instead of having only one sequence of functions as before, here we are taking the value of each point, feeding it back. And here we use an interpolation function to get only one of these signals, the one we are interested in. and to drive it inside the hammer function. This takes in the position of the point or the state of the point of the string that we want and outputs a force. And then we use another interpolation function to drive it to the string points exactly as we were doing before. Here then, to get only one signal from one point out, we interpolate out exactly like we were doing before. And let me just show you the process function for this example. This is just one big feedback loop. It's what's inside here. So one interpolation function, the hammer function, which is inside the FD library. Another interpolation function, the model, then a bus, and interpolating out. So just to let you hear how this sounds, let me increase again the number of points. Takes a while, of course. And as you can see, this is a bit more interesting than before. Okay, this is the end of the workshop, and first of all, I would like to thank you all for your attention. And since time was limited, I had to rush on some topics, so if you have questions or if you want to deepen some of the things I talk about, you can reach me at this.
Yeah, Ricardo, just be ready.
Yeah, bye.
To turn on your camera and...
Yeah.
Okay, well, great. Thank you, Ricardo.
Okay.
That was actually an awesome presentation as well. So much work. So much work.
Yeah.
I know.
Yeah, you know that.
So yeah. So congratulations about this. But so there is time for questions, and for now I don't see any questions in the chat. But do you want to say something or add something to what you've said? Or
yeah. So I wanted to say that well, I think I answered all the questions that I could on the chat. But what I showed, these are just the basics of finding different schemes. But of course, also more complicated things can be implemented. So and if you want, you can go see in the examples in the Faust ID, and there are some more interesting models that sound a bit more interesting. And as I said in the chat, if you want to explore more on finding different schemes, you can go and check out the book from Stefan Bilbao, Numerical Sound Synthesis. And one other thing that I wanted to say is about two-dimensional schemes. In this tutorial, I only covered 1D schemes. And you can, well, the library has the functions to build also two-dimensional schemes. But things are a bit complicated, as you Roman know, because the code becomes very complicated and very long. So if you put a very big number of points, then the code becomes very long, and the C++ compiler has some problems with that. So what I have to say is that the library allows to build 2D models, but if you want to take a look and you find some problems with that, that's probably the reason why you will experience some issues. Yeah, the last thing I want to say is that if you want, you can also by taking a look at the library, you can take the functions, the internal functions separately to build also, for example, nonlinear schemes, which are not impossible. Just the library is based on linear schemes, but yeah, there are many ways to explore those functions. Yeah, I think.
Cool, and I think there are a couple of questions on the chat actually. So,
Okay.
And there is one question by Am I Creative?
Yeah.
Does the routing get much more complicated for the 2D wave equation?
So about benching against MI Faust, I didn't really do that, but that would be really interesting. And especially to try to build a finely different scheme for a mass string, and then see how that compare. And yeah, I think that the approach I used is very much similar to the MI Faust one. So I think it would be pretty similar, but it's interesting to see. And any publications on that? Well, not yet, but well, let's see what will happen.
Yeah, and I think there is another question by Am I Creative? The
Oh, I
bonus
didn't see that.
question just right before
Oh
Alexander.
yeah. Now I see it. Does everything get much more complicated for the 2D wave equation? Yeah, like it's pretty much complicated, and that's the reason why the C++ compiler struggles a bit, because of course you have a lot more coefficients in the coefficient scheme, and that means that each equation block has way more connections, and the routing gets pretty much complicated. Yeah.
Cool. I don't think there are more questions.
Yeah.
No. Okay, well, great. So thank you again, Ricardo.
Thank you, Wolf.
Thanks for all this work. And we're actually going to take a break now for 1 hour, and we will resume at 7 p.m. GMT +1, not -1. Yeah, in the meantime, if you want to chat, you can go in the Google Meet meeting. I'm not sure if people actually went there so far, but it's there, like so if you want to chat in person, and not necessarily through the actual chat, you can do that. And so we'll resume at 7 p.m. With a presentation about the Faust physical modeling toolkit. So more about waveguide modeling in Faust, and then we'll have a presentation, the last one by Julius Smith, which will start at 8 p.m. About physical modeling in general in Faust. So take a break, have a drink, and see you very soon. Thank you.
Okay, well, welcome back, and hi to those of you who are just getting here. We're about to resume this Faust physical modeling workshop. We have 2 more sessions to go. The first one is going to be about the Faust physical modeling toolkit, which mostly concerns waveguide physical modeling and model physical modeling. And it will be followed by a presentation by Judy Smith, who will talk about physical modeling in Faust in general. For those of you who are joining us, you can ask your questions directly in the chat on YouTube. And there will be live Q&A sessions after both sessions where you can actually ask your questions live and get your reply live as well. Okay, well, so first session after the break will be about the Faust physical modeling toolkit. Hi everyone, my name is Romain Michon and I'm part of the Faust core team. This presentation, which is actually a tutorial, is going to be about the Faust physical modeling toolkit. There are multiple goals for this workshop. The first one is to give you an overview, a historical overview of the things that we've been developing as part of Faust for physical modeling for the past 10 years. We will mostly focus on the Faust physical modeling library, which is a library for waveguide and model physical modeling in Faust. And we will also be looking at Mesh to Faust, which is a tool that can be used to turn 3D meshes into model physical models that can then be used with the Faust physical modeling library to implement all sorts of musical instruments in Faust. So this tutorial is targeting pretty much any kind of audience. So we will start slowly by giving you some reminders about physical modeling in general, and mostly looking at waveguide and model physical modeling. And then we will go into more details and look at how these different tools actually work. And so the Faust physical modeling library, which is the first thing we're going to look at in this tutorial, is a library that allows you to implement physical models of musical instruments using waveguide physical modeling and model physical modeling, but in a modular way. So you'll see that we have mouthpieces, we have strings, we have bodies of musical instruments that can all be connected together in many different ways and in a completely modular way, which was not the case of the original Faust SDK. And this is going to be what the first part of this tutorial is going to be about. Okay, so before I move on to this, I just want to give you some reminders about waveguide physical modeling, because I'm pretty sure that some of you here don't really know how it works, So this tutorial is not about teaching you waveguide physical modeling, of course, but I just want to remind you about how that works. So if you look at the diagram here on the screen, you will see a waveguide model implemented. Well, here it's not implemented, but it's a waveguide model of potentially a string. And so the first thing that we need to ask here is, what is a waveguide? So a waveguide is just a structure that guides waves. That's it, And in any medium that you might use, like whether it's a string, it's a plate, or it's a tube or whatever, the material, the medium that you're using to drive the wave is going to have an impact on the time it takes for the wave to go from point A to point B. And depending on the material, it might go faster or slower, So basically, in signal processing and in the way we're going to implement that in Faust, a waveguide is just 2 delay lines in parallel. Because if you pluck a string, like if you take a string and then you pluck it, you will create two waves which are going to go in two opposite directions. One is going to go to the left, one is going to go to the right. So if you want to implement the most basic string physical model in the world, you need to implement first the fact that these two waves are going to go in two different directions. And on the diagram that you see here, the waves which are going to go on the right are implemented here at the top of the block diagram by two delay lines, the first one and the second one here. And we'll see later why there are two delay lines. And then waves which are going to go from right to left are implemented here on the diagram with the two delay lines which are at the bottom of the diagram. Okay, so the reason why there are two delay lines for waves going on the right and two delay lines for waves going on the left here is because we want to be able to introduce energy or to capture energy at the middle of the string or at any point on the string. So basically, what these two delay lines on each side of the diagram are going to allow us to do is to get the sound in the waveguide in different position. So basically, by diminishing the size of the delay line that we have here, we're going to be able to get closer to the left side of a potential string, for example, or a tube. And well, here it's a string because of the phase inversion at the extremity. I'm about to talk about that. And then on the other hand, if the delay lines here on the left are getting longer and the one on the right are getting shorter, we're basically going to pick up sound closer to the right side of the string. So basically, what these two couples of delay lines are allowing us to do is just to change the pickup position on the string. So we have we have waves going on the right, we have waves going on the left, but then we need to implement reflections at the extremities of the string. Because if you just take a string and you don't stretch it between 2 points, if you pluck it, it's not going to make any sound because you need to have reflections on each extremity of the strings in order for it to actually behave and sound like a string. And that's what those two multipliers that we have on each side of the string are for. And you see that they implement literally just a sign inversion, so just a phase inversion of the waves at each extremity of the strings. And that's because the waves in the string are transversal waves, and so when you get to the bridge, when the wave actually gets to the bridge of the string, then the string is going to go up and then it's going to go down like this, right? And so this literally just corresponds to a sign inversion. And we need to do that on the two extremities of the string, so on the left and on the right. And so basically what we see here is a very, very primitive, simple string physical model using waveguide synthesis. So one thing that is very important in waveguide modeling is this concept of bidirectionality that is very obvious here. We have things going in one direction and we have things going in the other direction. So going from left to right or from right to left. And so whenever we implement a physical model of a musical instrument, we're going to have to keep this bidirectionality all the way from the top to the bottom of the model. So for example, if you think about a violin, for example, or a guitar, so the string is connected first to the nut, so to the top, to the top of the bridge of the guitar, and then connected to the bridge itself, and then connected to the body of the guitar, right? And so all these things are coupled together. And because they are coupled together, they need to interact with each other, and that's why we need these type of bidirectional connection. So for those of you who already know Faust, you probably know that creating this type of algorithm is not necessarily very simple in Faust. Because in Faust you have the concept of feedback. So if you want to have the signal going in one direction and in the other direction, the only way you can do this in Faust is by using feedback and the tilde operator for that. And so that's how all the physical models of the Faust SDK were implemented. Most of them have a tilde and a feedback, which allows you to implement the waveguide. But if you want to create a system where everything is modular, so where you can put, say, a string here and then a bridge and a plug somewhere else, and you want to create a library which is completely modular in that sense, this is way more complicated to do in Faust because of this tilde operator, which is not a modular operator somehow. So when we implemented the Faust physical modeling library, the first thing that we had to do is to come up with a bidirectional block diagram algebra in Faust. So a form of algebra that would allow you to create this type of bidirectional connection in a very easy way without having to think too much about that. And if you look at the slide here on the screen, this is what one of the most primitive elements in the Faust physical modeling library allows you to do. And it's the chain element, and it allows you to create this type of diagram and this type of algorithm. So you see here that you have waves which are going from right to left. You have waves which are going from left to right. And you also see that there is a third channel, which is for the output. Okay, so some of you at this point might be wondering why we have that. Well, it's very straightforward because if you go back to the previous slide, you see that if you want to get the signal of something in the middle of the block diagram, and if you want to bridge it to the end of the diagram, because in Faust things usually go from left to right, you need a third channel to basically get this output here and send it to the end of the algorithm, bridge it to the end of the algorithm. And so that's what the third channel here is for. Okay, so let me give you a little demo of how this works in Faust. So basically, in Faust, you can use the pm.chain element. So pm is for physical modeling library, right? And so you have the chain function in the Faust physical modeling library, which allows you to create this type of bidirectional connection. Okay, so each element you're going to put in this chain has to have 3 inputs and 3 outputs, right? So one input and output for left to right, one for right to left, and one for the main outputs of the algorithm. So here what I'm going to do is that I'm going to create a multiply block. Okay, and so in this block what I'm going to do is that I'm going to multiply signals going from left to right by say 2, signals going from right to left by 2 as well, and then I'm going to leave the third channel just as a signal like this because currently we don't really need it. And then I'm going to be able to call that in multiply block, and I'm going to call it in pm.chain. Okay, and so here you can see the block diagram of this operation, which just looks like what we are expecting at this point. Okay, so now I'm going to create another block. Okay, and this block is going to be, for example, a delay block. Okay, and same thing, it needs 3 inputs and 3 outputs, and so I'm going to add a 10 sample delay. And here, of course, I assume that you know Faust already a little bit, so I'm not going into too much details in here. And so we have a second element here, which is for the left going for waves going from right to left. And finally, I'm gonna just leave the third third signal here empty, and now I'm gonna connect a delay block to multiply block. Okay, and so now you can see on the block diagram that we're creating something which is a little bit complex, but what this is doing, is literally just connecting things as you've seen it on the slide here, and so basically the first elements in multiply block and delay block are connected to each other. Same thing for the second one, and then we just assume that things are going in one direction and in the other direction. Okay. So this is very useful for what we're going to do next. So I hope you sort of get what I'm saying here, because this is really important. So typically in waveguide physical models, you're going to have things going in those two directions, but then you're going to need terminations so that you create some kind of loop, as on the slide with the string. Like you have those two terminations, the -1 and -g, and so eventually you want to be able to add that to your algorithm. And so the way you do that kind of stuff in the Faust physical modeling library is by using the L termination and the R termination functions. You can see here on the slide how they work. They take two arguments. So L termination takes an element A and an element B. And the element B can literally just be a chain or anything you want to give to it. And A is the actual termination. And same thing for R termination, but it works basically the other way around. So here is how we're going to use that here. So by the way, the algorithm we're implementing here is completely useless. It's just like to sort of give you an easy to understand example of how these actually work. So here I'm going to call pm.l termination, and pm.l termination expects two arguments. You remember there is one which is A and one which is B, and A is the actual termination. And here I'm just going to multiply the signal at the termination by -1, just like what we've seen on the block diagram of the waveguide. And then here, I'm just going to use a basic block, which are just 3 signals in parallel, basically, to make the system happy. So in practice, this element here is kind of useless. But we actually need to put it here if we do want things to work. Oh yeah, and of course, L termination needs to be fixed here. Okay, so here is the final product for this. So you can see that on the left side of the block diagram, we do have now a left termination. So everything that is going to the extremity of the waveguide is going to be multiplied by -1 here. And if we wanted to add a right termination here, we just have to do the same thing but the other way around. So we would call pm.r termination, and then we give a basic block here as the first argument. So we're gonna call it basic block. Okay, and then here we can do multiply by -1 again, for example, and now we have a right termination. Okay, so in practice, this is an almost complete model, and then if you want to end the whole system, because we still have 3 outputs, so we could literally just reuse this element in another chain if we wanted to, because we still have 3 inputs and 3 outputs. Now you can use pm.end chain to basically complete the algorithm, and now you only have 1 output and no input. Okay, so now we're going to try to make something a little bit more useful than the previous example. So just before we move to that, I just wanted to sort of give you a very, very brief tour of what's in the Faust physical modeling library. So if you go on the Faust library's documentation website, and if you look for the Phys models library, which is right here now on the screen, here on the left, you get an overview of the different functions that are available in the library. So the functions that we use so far are all in the bidirectional utilities section here. And you'll find the L termination, the R termination, the chain as well as many other things. But then as you start scrolling down, you will find elements which are much closer to musical instrument parts. So you will find a nylon string, you will find a steel string, you will find guitar nuts, you will find all sorts of musical instrument elements, basically, that can mostly all be used inside a chain to design musical instruments. So here you have the bowed strings section with the violin bow, you have the violin nuts, same thing for wind instruments here, etc., etc. So once again, the idea here is really to be able to take an element implemented in this library and then to use it in a chain to create new kind of musical instruments using physical modelings and waveguides. Okay, so in the next example, we're going to try to implement a string instrument, a pluck string instrument, using the library. And for that, we're going to use a function which you can find in the string instrument section, and it's the open string pick. Okay, so that element implements an open string. Okay, so it means that the string is not terminated yet. It doesn't have termination, so it doesn't have a bridge or it doesn't have nuts. So that's still up to us to add those elements. And what it says is that it's a bidirectional block implementing a generic string with selectable excitation position. It has a built-in pickup whose position is the same as the excitation position. So you can change the position of the pickup and of the excitation, but they are the same in this function. Okay, and that's what the excitation parameter here is for. So we're going to use this function. Literally what it implements is the same thing as what we saw in the slide earlier in this presentation with the 4 deal lines, 2 in parallel of each other, as we saw earlier. So let's try to use this, and so I'm going to start completely from scratch here in the Faust Web IDE, and I'm just going to create a new process line here, okay, and okay, so now the compiler is happy, and the first thing I'm going to do here is I'm going to create a function, and I'm going to call it myString, okay. And this function is going to have some elements, and I'm already going to use the with environment here because this function is going to have a fair amount of local functions, okay? And so I'm going to call it here on the process line, okay? So currently I'm doing something completely empty, but I'm starting a string, basically, and I'm going to use the Faust physical modeling library to implement that string. Great. So the first local element I'm going to declare here is going to be a chain. Okay. So I'm gonna call this my chain. Okay. It's a very bad name, but I'm gonna start by this. Okay. And this chain is going to use the chain element from the Faust physical modeling library. Like this. Okay, and so in this chain, I'm going to have to put some stuff, and the first thing I'm going to put is going to be an open string. And so I'm going to use the function that I just talked about, which is the open string pick function. Okay, and if we go back to the documentation, the openString function has 4 parameters. The first one is the length of the string in meters. And that's kind of a standard in the Faust physical modeling library. Usually you declare length and sizes using the metric system, and most of the time you use meters. You always use meters. The next parameter is the stiffness of the string between 0 and 1. The next parameter is the pluck position. And finally, the last parameter is the excitation. So the excitation itself. Okay, so 4 parameters. So first here, I'm going to declare a variable that I'm going to call string L for string length. And for now, I'm just gonna actually declare it here, and for now, I'm gonna say that the string is 1 meters long, which should make like a reasonably pitched string. Okay. The next parameter is the stiffness, and I'm declaring it here. Okay, stiffness, and I'm gonna say that stiffness for now is 0.05. By the way, like all these values are kind of empirical here, you know, like basically this is just a value for some kind of low pass filter inside the string, you know, like, so here I don't want it to have too much impact, so I'm just going to put 0.05 here. Okay, the next parameter is going to be the pluck position. So if we want this to sound sort of like an electric guitar, it's good to put a pluck position close to, say, 0.3, you know, because it's sort of like a third of the way on the guitar string. Okay, and so I think pluck position is a parameter that I want to make available here for people to control once the function will be actually completed. So I'm going to put it here. Okay, and finally the excitation. So of course in this scenario the excitation is going to come from the outside of this function, and it's probably just going to be an impulse. So I'm going to put it here as the last parameter of the function. Okay. And okay, so now the chain has an open string. Once again, that open string is what we want, but it's not terminated. It's open. So we still need to add a nut and a bridge on the other side of the string. Okay, so here on the left side, which we will consider here to be the top side of the string, we're gonna add nuts. Okay, and believe it or not, but in the Faust physical modeling library, you can already call pm dot elec guitar nuts. Okay. And this should just work. So now our chain has electric guitar nuts on one side. There are different types of nuts. There are acoustic guitar nuts, and so here we're using the electric guitar ones. If we had more time, I would show you how you can actually implement those, but we don't have time for this here, so I'm just using the existing function. If you're curious about how all these things are implemented, you know that the source code of the Faust libraries is actually available on GitHub. So if you go on GitHub and you look for physmodels.lib in the Faust libraries repository, you will find the source code of all the functions that we're using here. You know, so if you do a search on this page for, say, elec guitar. Oops, sorry, elec guitar nuts. There we go, elec guitar nuts, and you see the source code of elec guitar nuts here. Okay, so if you're interested, you can always check the source code of all these functions to know what's in there. Okay, so on one side we have nuts, on the other side we need a bridge. So here I'm gonna call the function called elec guitar bridge. And so now we have a string which is terminated. And if it's terminated, it means that it can actually make sound, which is what we want here. Okay, so great. So at this point, I think all we need to do is to actually give some values to the parameters that are not configured here yet. And so I'm going to configure the plug position to be, say, 0.3, as I said earlier, because that's a value that makes sense in that context. Okay, so now we have the string. We have the string, but we need to excite it. And to excite it, we're just going to create an impulse that we're going to send in the string. There are much more sophisticated functions to do that kind of stuff in the Faust physical modeling library. There are excitation models, but we're not going to use them here because, once again, the goal of this tutorial is to sort to give you a sense of how all these things work. And so if you're interested in that, you can just go back to the library's documentation to see how these things can be used. Okay, so here I'm going to create a button because we can do that in Faust, and I'm going to call it gate, of course. That's kind of a standard in Faust for a trigger. So I'm calling that one gate here, and I'm going to use the impulsify function. Function that basically turns the signal from a button into an impulse, right? I'm sure many of you already used that function before. And finally, I will just connect that to the string. Okay, so now we have an error here. And yes, well, I think there are multiple problems here. The first one is that in my myString function, I actually didn't call anything here yet. So I do need to put myChain. I'm sure some of you already caught this earlier. And okay, now I can see that I misspelled guitar bridge. Okay. Yeah, and so we still have errors because there is another thing that we haven't done yet. And that thing that we haven't done is that we need to terminate the chain. So we already did that in the previous example. And so in Faust, in the Faust physical modeling library, whenever you have a chain, you need to terminate it using the end chain function, and that's what I'm using here. Okay, and so now Faust is happy, and we do have something happening here. Great. So in theory, it should make sound. So if I run it, and apparently it didn't crash, and I click on the button, I do have a beautiful string sound. Okay, if you want to have it on the two speakers of your computer, you do need to do this, right? So that the output of the string is split, and that it goes on the two speakers of your computer. Nice. Okay, so now if we want to make this a little bit more controllable, we want to be able to control the string length in real time, right? And potentially assign a frequency to it. So how would that work in the Faust physical modeling library? The first thing we need to do here is, of course, to create a parameter for this string to control the length outside of the function itself. Okay, so here I'm going to create a length parameter, and this is length. And I'm going to pass it to string L that I have here. And now some of you might be wondering why I'm not just using length directly in here. Well, it's because in waveguide modeling, depending on what you put in the chain, because everything works with delays, especially the filters that are used to implement the electric guitar nuts or the electric guitar bridge. Because of all these extra delays, the string tends to be detuned a little bit, or at least out of tune. So the reason why I'm adding this extra step here is so that we can tune the string by hand, basically. Potentially, that needs to be done. Okay. So I'm going to show you how to do that after that. Now I just want to please the Faust compiler by basically setting up the actual length here. Okay, so I'm going to create a variable. I'm going to call it L. I'm going to say that L is equal to 1. Okay, and I'm going to pass L as a parameter to my function here, and in theory, still makes sound. That's great. Perfect. Cool. So as I said, the string here currently is out of tune. So the only way to tune it is to tune it by hand, you know, and so you just want to take a sine wave at 440 hertz or a pitchfork or whatever you want, you know, and you need to tune the string until it has the right pitch. And so so here, I already did it before doing this presentation, and I know that I have to subtract 0.11 to the actual length to get the right pitch. So you see that there is actually a fairly significant difference here between what we're expecting and what we need. Okay, so now it should be in tune, you know, and maybe it's not completely in tune. And if it's not completely in tune, you can adjust the value of this parameter here. But once it's adjusted, you know, it will be in tune for all pitches, of course, right? Okay, so finally, I want to control L with a slider. So I'm going to create a slider, and I'm going to call it freak, okay, in case I wanted to have a polyphonic string, because I will have freak and gate. You know that, right? And so for default, I'm going to say 400. Minimum, I'm going to say 100. Maximum, I'm going to say 1,000. And precise step of 0.01. I'm not explaining what I'm doing here because, once again, I sort of expect that you guys know Faust already. And so I'm just moving forward here. Okay, and so now how do I convert this frequency into a length? Well, there is a function for that in the Faust physical modeling library, and it's basically F2L. Okay, so now I have the slider, and I can control the pitch of the string that I'm playing. And so we have a string, and we could easily add a gain slider that we would multiply to the output of Impulsifier, for example, and then we could totally play that string with a MIDI keyboard. I'm not going to do that now because we're constrained by time, and I just want to move forward to the next topic. But you know, that could be a nice exercise for you at this point. Okay, so this is sort of the very general idea of how the Faust physical modeling library works. And of course, you can make things that are much more sophisticated and much more complicated. And in fact, it would be interesting here to go into more details to see how wind instruments are implemented, because it's slightly more complicated than just with a string. But the idea is always the same. You know, you use a chain, you put the different instrument parts in your chain, you connect them to each other's, and then you create a function around that, and in theory, in the end, you get sound. So the idea is always the same, and you can implement most musical instrument using this system. Okay, so now in this last session, I'm going to show you how to use Mesh to Faust to create physical models compatible with the Faust physical modeling library using Mesh to Faust and using 3D meshes, so basically 3D graphical objects. And you'll see that it's actually fairly easy. In fact, the hardest step here is to install Mesh to Faust on your computer. And I'm not going to document that in this video because you can find these informations on the Faust website. Okay. So here I'm going to use various softwares, and I didn't necessarily told you to install them before this presentation, but you can easily find them on their respective websites, and you can find these informations in the slide that is currently being displayed on your screen. Okay. So the first software we're going to use here is OpenSCAD. And OpenSCAD is one of my, it is not one of my, it's my favorite CAD modeling software. I've been using many CAD modeling software like SolidWorks, Rhino, and blah, 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 you know, and OpenSCAD is open source and it's free. It's very, very basic, very simple. But you can really do crazy things with it. It's super powerful. So if you don't know about it, I recommend you to give it a try. Okay, and it's also based on a functional programming language, you know, like which makes it great and really relevant to what we're doing here. Okay, so when you have OpenSCAD, you just create a new model. And so the goal here is we're going to model a metal plate in OpenSCAD, and then we're going to try to make a physical model from it using Mesh to Faust. Okay, so it's very easy to make such a model in OpenSCAD. Okay, let me scale that up for you here, because all we need to do is to create a cube. And we need to give it dimensions. And the dimensions here are going to be in millimeters. So I'm going to say that I want a plate, which is going to be 400 millimeters by 300 millimeters. So 40 by 30 centimeters. And for thickness, just 5 millimeters. Okay, and you need a semicolon here. And if you render that object, okay, there we go. We have our metal plate. Awesome. So, you know, this is a very simple example, you know, like, but it's just to show you how this works, you know, like, so we're done with OpenSCAD. We did what had to be done. Then in OpenSCAD, we need to render, so basically mesh that object, which is something we're going to do by clicking this button here. Okay, so this is done. Can take a lot of time if the model is complex model. And then we will export that to STL, and STL is a very standard format for that kind of things out there. And okay, and so I'm gonna, oops, no, that's not the right folder. Today it's not the Power Workshop, it is actually the Faust PM Workshop. Okay, and so I'm gonna save it here, and I'm gonna call that plates.stl, and I'm gonna save it. Okay, so now we're done with OpenSCAD. So you can save the model if you want. I'm not gonna do this, you know, I'm just gonna get rid of it because we have our plate.stl, and that's what we want to use. The next software we want to use here is MeshLab. And we're going to use MeshLab for a very specific reason, because you'll see that the mesh that was created by OpenSCAD here is a highly optimized mesh. And the problem of that kind of mesh is that it's not going to work for finite element analysis as we're going to do it with Mesh to Faust. And so here I'm going to get back to Faust PM Workshop, to the model that I just had, and I'm going to drag and drop it in Mesh Lab. Okay, just say okay. Now we have our plate, which we already had earlier. Okay, so this is our plate. And so in Mesh Lab, you can actually plot the triangles which constitute the mesh, and you see that for the top surface here, there are only two triangles, and that's what I meant by optimized mesh. Here, instead of having this, we want to have many small triangles that constitutes the mesh, you know, because we need to have like a high density mesh, which is not what we currently have here. So to do this in MeshLab, I'm going to use a filter, and so this filter is going to be found in the remeshing functions here, and so here what I want to do to increase the number of triangles that I have on the surface is uniform mesh resampling that you can find, I think, right here. Uniform mesh resampling. Great. So basically, the smaller this number here, the more triangles you will have in your mesh. And so for that example here, I'm gonna set this to say 3.5. I think that's the value that we want here. So, you can play with that. Like here, I'm putting 3.5. Actually, you know what? I'm going to put 4 just to be sure. And then I will just say apply. Okay. And now here in this window, I have a new mesh which was created. So I'm going to close the filter. And I don't remember which mesh is which one. Okay, so I think because you can hide meshes, and so here if I plot, yeah, there we go. So now you can see all the triangles, and yeah, okay, this one is the new one, and this one is the original one. So I'm gonna actually get rid of the original mesh. So I'm gonna say delete current mesh. Okay, and now I have this new mesh, which is relatively high density with a lot of triangles, and that's what we want to do finite element analysis here. Awesome. So there are other things that you can use here and other approaches to increase the density of your mesh and just like remesh it. I'm not going to go into details here, but this is all documented on this website here that is displaying on the screen. And you can find more information about other techniques in MeshLab to increase the density of the mesh. Great. So we're almost ready to turn that into a physical model. The one thing that we need to do first is we actually need to scale that model down. Because the problem is that it's too big. And so right now the unit is not right, basically. And so we need to scale it by a factor of 0.001. So here I'm going to go in filters, and in filters, yeah, I'm going to look for normals, curvature, and orientation. And I will then look for transform, and for transform, I'm going to select scale. Okay, and so here I'm going to scale the x-axis by 0.01, which will spread to, because I'm doing uniform scaling, so it will spread to the other axis. And then I can just do apply, okay, and then it will just disappear because now it's very tiny. Okay. So what I'm going to do now is I'm going to export that mesh as a .obj object, because that's what mesh to Faust is going to take as an input. And so I'm going to call my model plate.obj, okay? And then I will save that, and I will say okay, and we should be done. Awesome. So now I can close MeshLab, and I have my .obj object here. Okay. So the next thing I need to do is to actually use Mesh to Faust. And Mesh to Faust is a command line tool, right? So you need to use your terminal to use it. It comes with a Faust distribution. You can find it at the URL below in the Faust distribution. And you need to read the README to know how to compile it and then install it on your computer. I'm warning you, it's a pretty heavy tool because it relies on the MKL Intel library, which can be a pain to install on some platforms. On Arch Linux, it's super straightforward because it's part of the package manager, but on other platforms it might be really rough. So I'm warning you here. Okay, so I'm gonna go in the folder where I saved my .obj file, and it's the Faust PM workshop folder on my desktop. Great, and okay, so I have the plate.obj file right here. Okay, so all I need to do now is to call mesh to Faust. And I'm going to provide first to mesh to Faust an input file. So I'm going to say in file, and here I'm going to use plate.obj. Then I will specify the number of modes that I want to synthesize, because this is basically going to create a model synthesizers. Okay, and so here I'm going to say that I want only 50 modes. So the higher the number of modes, the more computation it's going to take, you know, like, so 50 modes means 50 biquad filters, you know, like, so that's already a lot, you know, like, so depending on the kind of application that you want to do here, you might want to decrease or increase that number. Okay, then I will specify the number of finite element methods modes. So basically the number of internal modes when mesh to Faust is going to compute the modes for the model. Okay, I'm going to say that the max mode, so the maximum mode, the highest mode, has a frequency of 10,000 hertz. So I'm telling the system to ignore all the modes that are above 10,000 hertz, so 10 kilohertz. Okay. Then I can specify the excitation positions that I want to integrate to the model. So how do I figure that out? So actually, if you reopen MeshLab on your computer, and if you drag and drop the plate.obj file that we created, great. Then you plot the grid of the model. So if you click here on get info, you can select any position on the model, and then it will give you the ID of the vertices corresponding to the triangle that is selected. So here it's very small and tiny because I have a high resolution screen, but I think if you press the P key on your keyboard, it will actually output all the informations that you need here. So you can select as many excitation positions as you want, and what you want here is to take one of the vertex position on the model here. So you see that here there's one that is 10,149, and that's the number that you would want to put in the terminal here. Okay, so I'm going to close that now. Okay, I'm going to put something fairly random here because we don't have a lot of time, so I'm going to say 5483, so 2 positions, and the other one's going to be 69 and 6959. Okay. Okay, I'm gonna say that I want this to be in debug mode so that more informations are plotted as the model is generated. And finally, I need to specify the material properties. Okay, and so you can find material properties easily pretty much anywhere on the web for wood, metal, any kind of material. And so the values that I'm going to use here correspond to copper, I think. So it's a very soft metal. And so if you want more information about this, just look at the documentation of Mesh to Faust. And so, yeah, these 3 values here correspond to copper. And finally, I want to specify the name of the model, and I'm going to call it plate. And then I can just press return, and the model will start being computed. That operation might take a little bit of time depending on how powerful your computer is. On my computer, it took about 5 minutes. In some very large models, it can take hours, so just be ready for it. And during those hours, your computer might run out of memory, and then it might just stop. Okay. So at the end of this operation, you end up with a .lib file. And so it's a Faust file. So you can open it, look at its content, and basically that's your model, model. Okay. So here, just to demonstrate this, I'm just gonna actually take this, copy it. Okay, so I'm selecting everything, I'm copying it. And then I'm gonna create a new file in the Faust web IDE, and I'm gonna paste the content of the .lib file in the Faust web IDE. So it's a .lib file, so it doesn't have a process line. And so I'm gonna have to add the process line here. So I'm gonna say process, and process is gonna be equal to my model, which is plate. You know, that's the name that I specified in the previous step. So this is plate, okay. And plate has several arguments, and the first one is going to be the excitation position. Remember, there are only two because we only specified two vertices on the model. So for now, I'm going to set that to 0 because we just want to hear sound here, right? So I'm going to set that to 0, and then you can specify values for the T60, which is the time of resonance of the model, and that's something that Mesh to Faust is not going to compute for you. So you just need to put like empirical values here, which kind of sucks because there are ways to solve this, but we never actually had time to work on it, and it's a complicated problem. So here I'm going to say that I want to have a maximum time of resonance of 8 seconds for the model. And then for the other values, I'm going to put 1 and 1. And there are just like decay ratios for the time of resonance for high frequencies versus lower frequencies. Okay. So now Faust is happy, and I need to drive the model. And to drive the model, I'm going to do the same thing as in the previous example that I gave you. I'm going to create a gate button, and I'm going to send that through an impulsify, and finally to the plates. Okay, and now if I run the model, and if I click on the button, beautiful, I hear my plate, and I'm going to send it to the two speakers on my computer here. Beautiful, great. So that's the plate. Okay, well, I think I told you everything I had to tell you for this tutorial. So you will be, of course, able to rewatch this video after the workshop. I hope you guys are having a great time today, and you can find more information about all these tools on the web because they are, of course, completely open source. So thank you very much, and I will now take questions on the chat. Okay, well, are there any questions? There are actually 4 minutes for questions, so I think the first, yeah, there are a bunch of questions actually. Yeah, can you have a muter position too? Well, the answer is no, because well, I guess that's something that could be added to Mesh to Faust, but yeah, it's currently not available. But it would be possible to add it actually. So definitely a feature to add. Next question: does the Intel MKL library work on AMD CPUs? That is also a good question. I don't really see why it wouldn't, but I'm actually not sure. But that is a good question. I would say probably yes, but I don't know. On Linux there is actually well, on Linux, on Arch Linux there is actually a package in the package manager for MKL, so it's very easy to install. So I assume that if they have it in the package manager, then it should be available for AMD processors. Not sure. Good question. Okay, then Sylvan is asking, are the excitation position the same as the listening positions? Actually, yes, and that's also probably something that we should improve one way or another. It should be actually pretty straightforward to change that. But yeah, currently, excitation positions are the same as listening positions. Okay, and I think that's it. So, well, if there are more questions because we are restricted by time here, feel free to shoot me an email, or you can keep asking them in the chat. Actually, there is one more question. I see it now. Like, does Mesh to Faust or the finite element model calculates relative amplitude of each mode shape? The answer is yes. There we go. So on the other hand, it doesn't compute the T60 of the mode, so the time of resonance of the mode, because we would need a damping matrix for that. And currently Mesh to Faust doesn't really support that, and that's something that we're planning on adding, like the ability to use a damping matrix for to calculate the T60 of the modes, but currently we don't have that. Okay, well, I think we should move on to the next and last workshop of today, which will be by Julius Smith, and it's about physical modeling in general in Faust, and I don't think there is a better person in the world to talk about that, so here's Julius's workshop.
Greetings, my name is Julius Smith. I'm the last speaker today, and wanted to talk about physical modeling in Faust. Start with a overview of models and their, the types of models we use, and then get into some examples. And I will build on the previous talks by focusing on what they did not focus on. So what is a model? You can think of a model as any form of computation that predicts the state at some future time of a physical object or phenomenon based on its initial state and any input forces through time up to the present time. And so this is diagrammed here. So we've got some object and we're driving it with a force, and we want to calculate what state it will have at time t. And then we have this notion of outputs of a system or of a physical model, and that would be some function of the state as well. So the purpose of the state is to summarize everything that matters about the object's behavior. It's the state of motion, its position, velocity, acceleration. In the case of electrical entities, it would be voltage and current. It's what you need to know to uniquely specify the state of the object, as opposed to its materials. So its materials would be fixed constant parameters such as masses and spring constants, capacitance, inductance. Those are fixed parameters of the system. The state is what changes naturally in normal operation. And that's what we need to simulate when we're simulating a system, when we're modeling a system, and when we're predicting its behavior, predicting its state through time. And so we only have forces coming in, but you can also effectively drive with other things. But ultimately it's forces. Even if it's a current source, you can think of a current source as a force through a very, very large resistor that will force a certain current. That's the way it happens in reality. So forces are general enough. There's only 4 of them, and that's all we have. So we will use vectors so that we have any number of forces. And for our world, the object is a musical instrument or an audio effect, like a circuit that emulates some effect that we like. And then we'll have the state, and that's also a vector. So there'll be some number of state variables that specify the state of the system. And then we'll form an output from the state somehow. And why do we want to do this? When do we want a physical model as opposed to just a recording, sampling, FM synthesis, additive synthesis? There are a lot of synthesis techniques. Why do physical modeling? Well, it's really nice when you want a lot of dimensions of expressive control. Now, it's easy to do that in general, in the abstract, because you can have any number of dimensions of any function. But when you have a lot of dimensions, you want to understand them. And physical models you can think of them as multidimensional expressions, formulations that we have lived with all of our lives. In other words, we lived in the physical world. We've played real instruments. We understand those dimensions. We know what it means to play a piano harder, to move a plectrum up and down a string. So these become very predictable. And when you have a lot of dimensions, the predictability is really valuable. And so the multidimensional expressive control is especially valuable for performing in musicians. The listeners don't really hear it. They don't know what you're going through up there. The audience members just hear the final music played, so they really don't know what the performer could have done or how constrained the performer may be. And so the performer can carve out a particular performance subspace of this high dimensional space and deliver a very unique and expressive performance, and one of a huge possible space of performances that are not available in a sample context. Well, it's not impossible in principle with sampling. You just have to do a lot of recording. Just think of how many recordings you have to make to capture a violin at every imaginable velocity, bow position, bow force, all the variable controls that you have, everything that can happen on the left hand. You have to sample every possible dimension densely enough that you can interpolate those recordings, and that's a lot of work. So if you have a model, it becomes a very small footprint, and you have all the natural expression, reaction to your performance, and it can run in real time. So we're lucky that we don't need advanced physics. We just need Newton's law, F equals ma. That's force equals mass times acceleration. That's really it. We don't need quantum mechanics. We don't need relativity. It's the most elementary starting point of physics. Isaac Newton started it out. And it's an ordinary differential equation. That's just a fancy way of saying that, the force equals the mass times the second derivative of position with respect to time, or the first derivative of velocity with respect to time. So there's a little calculus involved, but it's a very elementary equation. It's a first order differential equation in velocity. It's a second order differential equation in position. And it's an ordinary differential equation in that we only differentiate with respect to time. But when we talk about strings and membranes and spaces, then we have multiple derivatives. We have derivatives with respect to spatial dimensions, and that's when we call it partial differential equations. So it's still Newton's law, but we end up doing it in space as well as across time. So there's ordinary and partial differential equations, and that's really where it all begins. It's Newton's law, and then you use Newton's law to formulate your differential equations. And then we digitize those somehow. Because we have to implement everything on a computer nowadays, and so we will form difference equations or finite difference schemes. So we'll find some way to essentially numerically integrate our differential equations through time in order to execute the behavior of the model. And so the forces will come in, and the differential equations will tell us what the system does, and then we'll extract an output, and that's our physical model output. So even though this is a very simple equation, in the scheme of things, you can get very complicated very quickly when you combine a lot of them. When you have this is only one mass, okay? So when you have a lot of masses and they're interconnected by springs or other kinds of linkages, then you will have a very complicated situation very quickly. And so it opens the way for a lot of simplification approaches. There are a lot of interesting techniques that have been developed to tame the computational complexity in these various situations. So I thought I'd talk a little bit about the history, and I'm borrowing a very nice figure from Stefan Bilbao's book, Numerical Sound Synthesis, and it's a nice summary of the history of sound synthesis and physical modeling. And so the physical modeling is down here at the bottom, and that's what I'm going to talk about. And so, as I said, it started with Newton's law way back here, and then computers came along in the 1950s, and we had to discretize them or digitize them. And so we got into difference equations, and that's like a special case of finite difference methods. There are many, many kinds of finite difference schemes. Just think of how many differential equations there are, and imagine having 10 different ways to digitize them, 10 different finite difference schemes for each type of differential equation. It gets to a large number of things, and there's all kinds of methods for analyzing their relative merits. So here is where it forks off into one of the talks you've heard. So the mass interaction library comes from Claude Cadeau's in Grenoble, his work with the Cordes Anima system. And so that's a very early physical modeling system. It's in the category of finite difference approaches. And another very early example is Pierre Ruiz working with Laharan Hiller on applying finite difference schemes to bowed strings. And that was one of the things I cut my teeth on as a graduate student. I read that and was very interested in it. And it has progressed through time. Antoine Chen did much for the piano, guitar. And then there's just an enormous number of things going on out here in the form of finite difference methods for simulating physical systems. Very, very general. You can take any set of differential equations and numerically integrate them in some way. Another connection actually is wave digital filters, which you heard about earlier today from Dirk. The wave digital filter approach came along in the 1970s. Alfred Fettweis was the originator, and he was very influenced by Belovitch, who did a great treatise on classical network theory, which just incidentally is where digital waveguides came from. I was studying Belovitch when the idea for digital waveguide networks was born, and it was for reverberation, not synthesis, but it's just a very fertile book, this classical network theory book. And I believe that Fettweis actually worked with Belovitch. In any case, wave digital filters is from Alfred Fettweis, and it's a scattering formulation of analog circuits such as RLC, resistor, capacitor, inductor. Those are normally done as lump systems with just voltage and current, but you can also express the voltage and current as traveling voltage waves and current waves, and then you get the wave digital filter paradigm. And it's got excellent numerical advantages, and it's been used extensively for circuit modeling, and it's still one of the very best ways to go for modeling a circuit. And so now you've seen how that maps into Faust. And so you can see some of the cross connections here. Wave digital filters were also studied as an approach for general differential equation solving. That's back there in the literature. And so so that's a very rich vein as well. Now, the very earliest digital synthesizer that I know that actually was used to synthesize sound digitally, in a physical modeling way, was the Kelly-Lochbaum vocal synthesis technique, and it's basically a transmission line model for the vocal tract. And Max Matthews, the father of computer music, did the musical accompaniment in the very first demo that we know of by the Kelly and Lochbaum method, and I have that on my website. I have it in other talks, and you can find it and play it and hear it. And they were working towards speech synthesis. So this was work at Bell Labs, and Max Matthews was director there. And they did an amazing demo of speech in the 1961 timeframe. And so that research actually seemed to sort of go in pause for quite a while, but then it revived in later years. Perry Cook gave it a big shot in the arm with his thesis on using this approach to essentially as a singing voice technique. I came up with digital waveguides, as I mentioned, based on Belovitch, but sort of in retrospect, realized that it could have also have been discovered as an extension of the Kelly-Lochbaum approach, because all you have to do is erase a lot of the scattering junctions in the Kelly-Lochbaum formulation, and you'll get digital waveguides out of it. So in both cases, you have scattering, but what the Kelly-Lochbaum doesn't have delay lines. It just uses single sample delays. And another thing you can derive as a special case in retrospect is the Karplus-Strong algorithm. And so that's here. And so all these things, connect together. There's a lot of independent reinvention going on, and a lot of connection going on. But when it all comes down to it, it's Newton's law. Now this approach up here in also wave digital filters is based on a wave formulation, and you do go from Newton's law to waves, but you have to formulate the wave equation for the string, and then you have to solve it to get the traveling waves, and that was done by D'Alembert in I believe it was right before Bach died. So it's way back there as well. And so there are ways you can describe it as arising from that and coming out this way. So we have two main formulations, sort of the lumped formulation involving masses and springs, and you do finite difference schemes based on that. And then you have the wave-based approaches, and that's the Kelly-Lochbaum, Karplus-Strong. Well, Karplus-Strong was not a physical modeling approach, but it was interpreted that way, years after it came out. It was interpreted physically as a transfer function approach at the time, but that once again, things connect in retrospect. So here's and then wave digital filters is a wave-based approach, and it's a very interesting case of a wave scattering formulation of a lumped system. So it's essentially a wave environment where the speed of wave propagation is infinity, which is very unusual. But it's got wonderful properties because of the scattering formulation. It ends up having excellent numerical properties, for example. So then up here we get to Max Matthews starting computer music, and it started out with wavetable synthesis, which is just a small, one period in memory that gets read out over and over again at different rates to get different pitches. And so this goes into other synthesis traditions that I will not get into, except I will talk a bit about modal synthesis, because modal synthesis can be derived as a physical modeling approach. So if you have a physical system and it's got resonant modes, then it will spontaneously decompose into a sum of resonators, and that's what you have in modal synthesis. And the only real difference between how it was practiced originally as a synthesis technique and coming from physical modeling is that you know how to drive the modes, and you know how to combine the modes to reproduce a particular physical scenario. So like if you move your drums around, you move your sticks around on a drum, you get different mode excitations. And if you put your pickup at different locations on a drum head, you'll get different combinations of modes. And that's what all comes out automatically when you formulate it as a physical model and then convert it into a modal synthesis. And I'm going to talk a little bit about that today. And then if you let the damping go to zero in the modal synthesis, you'll get additive synthesis. You'll just get a sum of sine waves, and these things all interconnect, and I could go on, but I'll try to stick to where I should be here. That was some history. So here are the formulations that I know about. There are probably more out there, but I already mentioned ordinary differential equations. You differentiate with respect to time. Partial differential equations, you have derivatives with respect to time and space, 1, 2, or 3 dimensions. Although we can go to more dimensions if you want to hear things in 10-dimensional space, why not? And then if you digitize them, you get what you could call difference equations, but the more general name is finite difference schemes. And I would say difference equations are when you directly digitize differential equations by some simple, substitution, like first order difference for a derivative, that kind of thing. But finite difference schemes go much beyond that. In other words, like just look at fourth order Runge-Kutta to get an example of things that are not just a simple substitution for a derivative. And I already mentioned transfer function modeling. So if you know the physical input to a system and the output, and it's a linear time invariant system, then you can get its transfer function. And that's how I was modeling strings during my thesis years. You know, you would excite a string, and its transfer function was known. You know, it's e to the s t, where t is the delay. And so that was the transfer function approach. And it's also very common in classical control theory. So classical control is based on transfer functions models of what they call the plant. So the system is always called the plant. And in our case, the plant would be a string or a bore of a woodwind. And so transfer function models were big. They were used extensively. But at some point, the control systems reformulated as state-space models somewhere around the 1960s, around the time of the Kalman filter. The aerospace program was adopting them. They were using them for satellite tracking, that sort of thing. And so state space became the standard formulation for control systems. And so that's when they started calling this old transfer function modeling approach classical control. So yeah, classical control and what we do now. And state space models are still really big. In particular, they're really big in the MATLAB world. And there's a whole story there about how MATLAB was, originally developed by Cleve Moeller at University of New Mexico, and he just wrote it as a desk calculator front end to his numerical linear algebra libraries, things like IcePack and LinPack. These were subroutine libraries in Fortran for calculating eigenvalues and linear least squares solutions. And so it was a really neat language for running experiments. It had no files, had no functions. It was really a nice little interactive desk calculator interface to the subroutine library. And then a number of people picked up on it and took it much further. And I worked at one of those places, Controls Systems in Palo Alto. And Control C was the name of the competitor at Integrated Systems. So there were a lot of people working on this. So our company was Systems Control Technology, and we were working on what was MATLAB for control systems, and that's the reason it's probably the dominant component of MATLAB today. I haven't checked that out, but every time I've checked, it's been the dominant library space, and that's important to know because it means that the state space approach is perhaps the most supported approach in terms of computational support from systems like MATLAB. Now, if you take a state space model, it tends to be a little expensive. It can be, although Jan Orlari did some interesting benchmarks that showed that for the cases we tried, such as a biquad filter, the state space model was about the same as just a normal direct biquad implementation using direct form 2, the standard things that are in the libraries. So that's because these are sparse matrices and the compiler is good at optimizing and not computing anything unnecessary, so that you can hope that your state space model will run at the same speed as your ordinary transfer function model. But that doesn't normally happen without some good optimization going on, because your state space matrices are order n squared, where n is the order of your system, whereas your transfer functions have coefficient order n set of coefficients. So you have to be careful to not spend more time doing the computation. But what people very often do to guarantee that that's not a problem is that they diagonalize the system. So there's a thing called a similarity transform. You get the matrix of eigenvectors of the state transition matrix, and that gives you a transformation matrix that will then take you to modal coordinates, where all the modes are vibrating on their own axis, so to speak, in the space, and then it's a diagonalized system, and everything's in parallel. So it's a set of one-pole systems in parallel. But unfortunately, the poles can be complex. So what we do is we combine the complex poles to get biquads. So you make a parallel bank of biquads, and that's what we usually call the modal representation. It's just a set of parallel second order filters, or first order and second order. And so that's a very common final form of a state space model. And then some other representations that are used a lot are equivalent circuits. You'll maybe take, let's say, like there's a really classic paper on the violin as a circuit by Schelling. It's something that was done a lot, a century ago. And, you would just take a physical system or an acoustic system and come up with the equivalent circuit for it. You can find equivalent circuits for the ear in various, the basilar membrane of the ear, the way hearing works. So there are all sorts of circuits out there, and so it's nice to be able to digitize those. And a good way to digitize a lot of systems is to first get the equivalent circuit and then digitize that circuit, because there are very nice systematic methods for digitizing circuits, specifically things like the wave digital filter digitization of circuits. Impedance networks are also valuable, and probably don't have time to get into them, but I just wanted to put it down here because I think it's an important representation, and it's used for circuit analysis. So if once you have your equivalent circuit, you can now replace every element in the circuit by its impedance. And if it's a linear time invariant circuit, you can do very elementary resistor analysis of the network, because you can manipulate the complex impedances of things like inductors and capacitors as if they were resistors when you're in this impedance space. It's like taking the Laplace transform of everything, and in the differential equation space, it turns the differential equation into an algebraic equation. So your ordinary differential equation just becomes a polynomial in S for the analog case, continuous time, and it becomes a polynomial in Z for discrete time, and those are a lot easier to work with. And then there's wave digital filters and digital waveguides. All right, so those are the main formulations, I would say. Okay, so let's talk a little bit about state space models. We can start with the equations of motion for some physical system, and then formulate it in a state space form where we have the state x, which is a vector, is combined with input forces to give us the derivative of the state. And that means it tells us where the state is going. And then you can integrate the state derivative to get what the state's doing. So this is, you can think of it as kind of like a generalized mass. It's like a vectorized mass. Because this is the way a mass behaves. You apply a force to a mass, and F equals ma. So you can see that the force divided by the mass gives you the acceleration, and then you can integrate the acceleration to get the velocity. So if we choose the state variable to be velocity of the mass, and the input is a force, then the acceleration comes out, and we integrate it to get the velocity, and then we are therefore choosing our state variable to be the velocity. But the point I'm making now is that this is very, very general. This is by vectorizing the state variables and the inputs and the force, the force inputs, we're representing an arbitrarily large system. You can even model the brain in this form as a state machine. About the only thing we've really conceded here is that we're assuming causality, and that's just life in the world, right? You can't predict the future, so this is extremely general, but it is constrained to not be able to predict its future inputs, and so the future behavior of the system can only be a function of its current state and its current inputs, and anything about the past inputs is summarized in the state. So the state is a sufficient statistic, so to speak, for the entire history of inputs. So all we need is the input now and the state now in order to predict the system for all time, if there were no further inputs. But there'll be more inputs, and so we'll need those. Okay, when defining a state space model, you want to choose states that provide a physical amplitude for some energy storing degree of freedom. As an example, for a mass, you would not pick the velocity and the position, even though those are very important. You would think of those as being necessary to specify the state, but the position does not store energy, only the velocity. So the kinetic energy of a mass is 1/2 mv squared, where v is the velocity. For position to correspond to energy storage, there would have to be a spring involved, and we associate that energy with a spring. So you would have position and velocity as state variables in a mass spring system. So just think of a state variable as the physical amplitude for an energy storing degree of freedom, such as the displacement of a spring or the velocity of a mass. And you get one state variable for each energy storage element, each spring, each mass. And notice these are what we call lumped elements, as opposed to distributed elements such as vibrating strings, which you can think of as a continuum of masses. It's an infinite number of masses in principle. It's the limit of a mass spring chain, and the limit is the masses go to zero and the springs go to zero very close together. So in a circuit, in an RLC circuit, you get a state variable for each capacitor and for each inductor. I can't highlight, there it goes. And so then when you discretize, you'll have a state variable for each units of delay. So every sample of delay is an energy storage element. It holds one sample, and its energy is proportional to the square of that sample. That's the energy in one sample, the power, you could say. And the actual units matter. So it's usually the square of the sample divided by the impedance that it's in, if it's a force or a voltage, that sort of thing. Okay, and then the number of state variables is the order of your system. It's the order of the polynomials. Transfer function, if you look at the transfer function, and it's the order of the matrix, the state transition matrix in the state space model. So that's just a summary of state variables. And now you can get the modal representation from the state space representation. Let's just jump to that real quick. So let's say we have a linear state space model like this. We can diagonalize it. So all we need to do is find the eigenvalues of the state transition matrix. And eigenvalues solve this equation, that the matrix times the eigenvector. The matrix times the eigenvector is the eigenvalue lambda sub I times the eigenvector E sub I. And so if your poles are distinct, if the eigenvalues are distinct, then you'll have a set of linearly independent eigenvectors, and you can form the similarity matrix, the transformation matrix. So you just put all the eigenvectors side by side in a matrix E, and that is your transformation matrix. And if you don't have distinct eigenvalues, then there are things you can do. You use generalized eigenvectors, and it works out. And you can look that up. In MATLAB, you've got you've got the eig function for finding the eigenvectors and eigenvalues, and you can use that to diagonalize the system. So you're essentially changing coordinates. So this is our original state vector, and we define it as the matrix E times a new state vector, which is in modal coordinates corresponding to the diagonal system. And so we have an identical state space system in form, but we have transformed to a new set of coordinates, which are the modal coordinates, and the new matrices are given by these formulas. So there's no change to the feed around term, but you have a new C matrix and a new B matrix and a new A matrix. And this is called a similarity transform, and it does not change the eigenvalues. It's the same system, but it's been it's gone through a change of coordinates. It's called a similarity transform. And so the transfer function of this system is exactly the same. But the big advantage is this is a diagonal matrix. You've diagonalized the matrix, and it follows directly from the this equation right here. You can use that to show that this matrix diagonalizes the system. Very quick derivation. And so if it's diagonalized, it's more efficient. You can implement your system as a bank of complex one-pole filters, and you can group the complex conjugates one-poles together and make biquads out of them. So you can have a parallel bank of biquads, and if they're real poles, you can just leave them as one-pole filters. So that's usually what you do if you're really using state spaces, diagonalize it. Now that also requires linear time invariance. These transformations are not so easy if you have a system that's changing. If it's a nonlinear system and your elements are varying, then you would want to do all this in closed form. You have to keep track of everything. So we normally only do this for linear time invariant systems, or at least linear. We don't want to be doing closed form operations for matrix elements that might change. Okay, so that's the modal description right there. And on this MATLAB page, it shows you an example of modal canonical form. So this is for the continuous time case, which is looks the same in most ways. So here's the eigenvalues. So you have two real eigenvalues and then a complex conjugate pair of eigenvalues. And in the discrete time case, that would be e to the plus or minus j omega t times r. R would be the coefficient corresponding to the damping sigma. And then the real case is just real. And then you can see there's a real eigenvalue here, a real one there. And this little 2x2 block is the biquad. And it came out looking like this. But this can be any little 2x2 state space matrix. What we saw was minus A1, minus A2, and 0 and 1 on the bottom. So it's whatever you want there. There are a lot of different forms there. It depends whether you started with direct form 1, direct form 2, normalized, lat. There are all these different forms. You can get a lot of different things here. But whatever it is, it pulls out now as a separate subsystem. So you can now implement this as two parallel one-pole filters and a parallel biquad. And the B matrix and the C matrix will change as a function of how you choose this form in the biquad stage. But whatever it is, you just pluck it out and implement it separately. So that's usually what you really do. So now we're ready for the example. All right, let's take a look at state space modeling in Faust. All the other approaches except state space and modal synthesis have been covered in other talks. So I'm just going to do state space, and then, as I mentioned, if I diagonalize the state space model, I've got a modal model. So the digital state space model is written like this. So Y is a vector output. It's just any number of outputs is some C matrix times the state vector, X underbar, plus D times the input signal. And the D is direct. It goes around the system, actually. So Y is getting a direct feed from the input that bypasses the state completely. Now the state update is here. This is for the discrete time case. I showed the continuous time case where you get a derivative as the output, and then you have to integrate that to get the next state. Here we just jump one sample forward and calculate that. So you can think of this as having numerically integrated derivative for one sampling interval. So the state at time n plus 1 is the state transition matrix A times the current state plus the B matrix times the inputs U. And here's everything all written out. And so I'll just say we have capital N states. That's the order of our system. It would be the number of poles in the transfer function of the system. And then we have any number of inputs P and any number of outputs Q. And so that forces all these matrices to have these sizes. We can observe that the matrices B, C, and D are feed-forward matrices from the input to the output. And the A matrix is a feedback matrix. Everything else is feed-forward. A is feedback. And a really important point here is that all four of these matrices can change every sample. So this is a very general implementation of time-varying linear systems. We're still constrained to linear because of this structure here. So the output is a linear combination of state variables plus a linear combination of inputs, and the state update is a linear combination of the current state plus a linear combination of inputs. So we're staying within the space of linear systems, but it can change every time instant. We're also staying within the realm of causal systems. So we still have no ability to predict the future here, So we're dealing with linear, time-varying, causal systems of any type. Okay, so here's some Faust code that will do this. Let me go into this mode. So we're going to have 2 inputs, 3 outputs, and 5 state variables. So it's a 5th-order system, and I will put this code in the comments down below, so or a link to it, so you can download it and try it if you want. So we have 2 inputs, 3 outputs, and 5 state variables. And so I've defined a little function down below that will define a matrix. So this is an n by n matrix, and then we have all these other matrices. They're various sizes, and here are the definitions of those. Here's the definition of matrix. You can take a look at that. It's not unlike the example in the Faust distribution that's already there. And these are the there's one little detail here that you need to delay the B matrix in order to get the standard definition of state space and discrete time. And I'll show you on the figure, the block diagram. It's easier to see it there. And so we define this vector sum here as a bus that then interleaves down to a bus of length n, and that will sum 2 n vectors for us. And here's an impulse that we'll use for setting the initial conditions. We want to be able to have an arbitrary initial state. Usually a state space system will allow you to specify an arbitrary initial state, and then everything after that is just the inputs coming in. So here's our initial state. It's we're just arbitrarily setting it to 0 through capital N minus 1, and the impulse, make sure it only happens at time 0. This is just for the example. But you would put, instead of I, you would put whatever your actual initial state variables are here. And then here's our system. So whenever I'm writing Faust, I always like to fix the number of inputs and fix the number of outputs. So I start with a bus of size P because I want P inputs and nothing else. And for the outputs, I want Q outputs. And so then we'll fan out to the D matrix, which is going to go up and over directly to the output. And then we have our this is what I would say is the real heart of the state space system, where we come in through the delayed B matrix and go into a vector summer with the state, and then that feeds back around through the A matrix, the state transition matrix. And then on this other parallel branch, we have our initial conditions going into a vector sum with the C matrix multiplication, and then all that fans down to the outputs, Q outputs. And so process equals system. So let's take a look at the diagram for that. That's funny. The mode changes when you're in this mode. All right, so here's the state space model. 2 inputs, 3 outputs, and 5 state variables. 2 inputs. Here's our delayed B matrix. See, the reason this is necessary is because these delays introduced by feedback do not affect the feed-forward path. And so we have to put it here. What I'd like to do is just push these delays into this branch, and then I could use a normal B matrix here. It's just a matter of definition. That's all it is. So the state initial condition comes in here, and it fires at time 0. Remember, it's got those impulses multiplying it. It's multiplied by an impulse, you could say. So it only fires at time 0 and goes into the C matrix at time 0. And then this delayed B matrix holds off the input for time 0 because it should not affect the output at time 0. Anything that affects the output at time 0 from the input goes this way. Okay, so the D matrix takes care of any direct bypassing the state dynamics part. All right, so here's our B matrix. It comes in. So this is your state. So these delay elements contain the state variables, and the A matrix feeds back around, and then you sum. So this is x of n plus 1 summing with B times U, the input, and that forms the next state. And then the C matrix takes a linear combination of the states and puts it out. On the first sample, time 0, it's C times x0 that goes out. That's your time 0 output. you also add d times u to that. So time 0 is very different from everything else. It's x0 plus b plus u, d times u. And then after that, you're looking at the input through b, and the output is c times the feedback. I want to tell, I'm about to say the transfer function, but that, I guess I could say, yeah, c times si minus a inverse, or zi minus a inverse times b, but that's not fair because I haven't derived that for you. But you can see right here what it's doing. Let's go back to this mode. There we go. All right, so to use this, we have to get these state space matrices. How do we get our A, B, C, D matrices? And it's actually very straightforward. What you do, let me jump to an example here. This is a biquad in direct form 2. This is a basic direct form 2 digital filter order 2. So you just write it down any way you want. So you just write down any block diagram, and then you go find your delay elements, and those are your state variables. Every delay element contributes a state variable. Now, if you have a delay line where there's nothing going on, let's say I didn't have these lines and it was just a delay line, you can handle those as one unit. And if you've ever looked at feedback delay networks, then you've seen this before. Feedback delay networks are essentially written in state space form. They're analyzed in state space form where you have generalized delays of any size. So in normal state space, these Z inverses are always Z inverse, but in a feedback delay network, they can have arbitrary size. And that's used a lot in the reverberation world. So, but you can also just go ahead and label every single element of the delay line, and that would be the strict state space model. And so that's what we have here. And so you go just arbitrarily number them. You know, I could interchange 1 and 2 here. It doesn't matter. That's why it's not unique. But if you tend to be systematic, you'll tend to get about the same thing. And so these are our state variables. And now you're ready to write down the state space matrices. So think about X1. All right. What do we need? We need to know the state update. So we write X1. So we're looking at the state update. So we want to write X1 of n plus 1 as some linear combination of the input and the state variables. And we know that's possible because by definition, the state summarizes the system at time n. And so the only thing X1 of n plus 1 can possibly depend on are the state variables and the input. And so we just figure out what that is. And so you see that X1 of n times n plus X1 of n plus 1 is going to multiply U of n times 1. And it's going to multiply X1, the previous value, by minus A1. And we're also going to have minus A2 times A2. So we can see that down here. So B, the first element of the B matrix is 1, and that's this path right here. And the top row of the A matrix is minus A1 minus A2. And so you see that. So you can just read it right off the block diagram. You just trace the lines in the diagram. And now the C matrix is a little trickier. So the C matrix is what is our linear combination of the output? I mean, it's still the same thing, but you just have to watch out for feedback, okay? So looking from Y, we see that it's got B0 times, so we can't use this. We can't say X of n plus 1. We've got to find the combination of X1 and X2 at time n. We're not allowed to use n plus 1. You can do that, and you'll get interesting algorithms that way, but they're not standard state space. They're important algorithms that do that kind of trick. But that's a different subject. So what is it really? Well, you do see B0 times U. So you now found our D matrix, right? So there's a direct term, B0. So D is equal to B0. That just jumps out at us. But what about what is the function of the state variables? Well, we have to go through this summer and see that we've got the minus A1 here. And it also gets multiplied by B0 before it gets out. So X1 goes through minus A1 and then B0 before it hits the output. And so that's this term right here. And then this is the other thing to watch out for is that it can be used twice. So it got used once as a feedback and then secondly as a feed forward. So we actually have two terms here for the first output, which is B1. So we're talking about the coefficients of X1 making it to the output, which is the first element of the C matrix. And so it's B1 times X1 plus B0 times minus A1 of X1. And so these are easy to accidentally overlook. You just have to be careful. And then it's the same story for the second state variable. It's B2 times that state variable plus minus A2 times B0 times that state variable, and we're out. Okay, so that's how you fill in the matrices by direct inspection, and that's all I've ever had to do. I've never had to do anything more fancy than that. But there are, fancy software systems for taking various canonical forms and cranking out these matrices. There's all sorts of tools out there. MATLAB probably has most of them. Okay, so let's look at a state space example for the biquad in Faust. Here we go. We will start out with just getting the biquad together. We pick a pole radius of 0.9, a pole angle corresponding to the sampling rate divided by 10. And this is the normalized radian frequency formula and the denominator coefficients of the transfer function, which go into the top row of the state space matrix. You've probably seen these expressions before. If you've worked with digital resonators, they come up all the time. And then this is the numerator. Just arbitrarily chose a 0 at DC and half the sampling rate. It's a very standard case for the biquad. You have a resonator with no response at DC or at infinity. Those are the zeros there. And so here's the direct form case, just straight out of filters.lib, TF2. And now here comes the state space case. And this is a very simple case with one input, one output, and two states, second order system. And so this is using pattern matching to set the coefficients. A11, A21, etc. So we have our denominator coefficients in the top row. This is one of the canonical forms for 2 by 2 states. Well, for a state space matrix, you have the denominator coefficients across a row. It can be the top row, it can be the bottom row, it can be the right column. There are various controller canonical forms, observer canonical form, all those canonical forms. And actually, I happen to have a page from MATLAB on canonical state space realizations. It's a good place to look. So there's companion canonical form, observable, controllable. And so, yeah, you can see that companion form has the denominator on the right. The companion matrix is the state transition matrix, the feedback matrix. And so the observer canonical form uses that companion matrix and defines the matrices like this. It's observable because it's got only one output. So you can't introduce zeros with only one output, but you can have zeros on input. So your inputs can encounter nulls going into the states. So you don't necessarily have controllability of all the modes, but you do have observability of all the modes. This is just, a little by the way on state space stuff. And then there's controllable canonical form, where you have only one input coefficient. In other words, all this is the single input case, and all the input goes into only one state. It doesn't go to a bunch of states where you can induce zeros. But the flip side is your output is a linear combination of states, and you can introduce zeros, and there would be no observability at those frequencies. So you don't have guaranteed observability. So that's where the terminology comes from, and you can pick whatever form you want, but the form I'm going to talk about, well, we're going to get whatever form we get by just analyzing the block diagram, and it will turn out to be essentially the companion form with things flipped around. So the controllable canonical form has everything on the bottom, all the denominator coefficients of the transfer function. By the way, this is all continuous time. The discrete time case is similar. It's not that different. So we found it on the top row. So what we had was a controllable canonical form with a permutation. It's just like renumbering the states oppositely. So, to just flip this up down, you would just renumber the states in the opposite order. So here we are just entering those numbers, and you can see that we are controllability canonical, because we're feeding into one state. Can't introduce zeros that way, but the output could have a zero, so it's not necessarily observable. And then we have a feed around term. But we're just making a biquad using a state space model. We're not really concerned about it. But just intuitively, it's reasonable to know that your controllability and observability of a system have to do with whether or not there are zeros in the way. So if there's a zero canceling a mode in your system, then you can't control it, you can't observe it. And so you can see that it's different whether you're going in or coming out as to whether you have a zero coming in or zero coming out. Just a little by the way on state space. All right, so now this is the definition of the matrices, and we will, and remember we derived this directly from the block diagram. These are the matrix entries that we derived from the block diagram by inspection. And right now you also have to define, using in pattern matching, you set a formula for different arguments. So so b of 1, 1 will get rewritten to 1, and you can have more rules for different cases. So b of 2, 1 gets rewritten to 0, and we're not writing anything else. Well, right now the Faust compiler requires you to have more than that, and so I'm just putting some arbitrary definitions for, but these rules follow the previous rules, so they are, lower priority. But if we didn't define any of these, then here's a catch-all definition, and that's presently required. That will probably go away. And then this is the definition of the matrix, and we've seen this before, and this is all the same. So that's just the same, general code for state space, and that's the Faust example. And so up here you can compare it. This is what I did to test it. I compared the direct to the state space and then differenced them and found that I got 0 to within machine precision. So for double, it's better than for single, and then for quad it's even better. And so that's always a good test. Okay, to conclude, we talked today about a number of physical modeling formulations, and here they are again. We're now the ones that are suitable for computer implementation are italicized, and these are the ones we talked about today in this workshop. So earlier we had talks on finite difference schemes, wave digital filters, and digital waveguides, and in my talk we saw some state space modeling and modal representations obtained by diagonalizing the state space model. And that covers quite a bit of ground, and hope you enjoy your models, and I look forward to hearing what they do.
Okay, well, thank you very much, Julius. I think we have plenty of time for questions now, because this was the last presentation of today. So, Julius, actually, are you here? I think Julius is probably still watching the end of the presentation and what's happening on the live chat. So yeah, there's like a 20 seconds delay between reality and what you guys actually see. So
are you here?
I am, but I don't.
There you are. Okay, great. Yeah, I can hear you very well, actually. Probably still watching the end of the presentation and what's happening on the live. You should turn it. Yeah. Okay. Yeah, Julius?
Yeah.
I am.
There you are. Turn off. Yeah, I can hear you very well, actually.
Still watching the
That's-
end of the presentation. What's
I'm here.
happening live?
You should turn off the live stream.
Actually, me in the past. Can you hear me now?
Yes, now I can hear you very well. There we go.
Can you hear me?
Julius?
Yeah.
No.
There you are. Turn off.
This is the most
Yeah, I
bizarre.
can hear you very well, actually.
Still
I'm gonna-
watching the end of the presentation. What's
I'm here.
happening live?
You should turn off the live
There's some
stream.
loop. Actually, me in the past. Okay. Can you hear me now?
Yes, now I can hear you very
Can you
well.
hear me
There we go.
Can you hear me?
Julius?
Yeah.
No.
There you are. Turn off.
Oh, there's a
Yeah,
most
I can
bizarre.
hear you very well, actually.
Okay.
Julius, can you hear me?
I think I severed the loop, but I can't hear myself yet.
Okay, but you can hear me, right?
I can't hear you.
You can or you can't?
What's going on here? Okay, let's go to this.
Okay, can you hear me now or? Julius, can you hear me?
Tell me if you can hear me. Can you hear me?
Yeah, I can hear you very well, but can you hear me?
Can you hear
Can
me?
you? I hear
I'm gonna try to
you very well.
I got my camera on.
Okay.
Supposedly I'm there.
Yeah, but can you? Can you? Yeah, Julius, can you hear me? Julius?
So bizarre.
Hello?
Wait, I know what to do.
Um,
I hear you now. Can you hear me?
no, I can hear you. Yeah.
Oh, okay. I can't
Great.
see anything. I
Okay.
can't see anything. Well, that's weird. I got caught in an eddy in the space-time continuum.
Yeah, well, you know what happened? You probably had the live stream on, and so you were
Yeah.
hearing everything that I was telling you with a 20 seconds delay, basically.
Okay. Well, yeah, but I had this chat session open in Chrome, and when the live stream ended in Safari, I just left it for dead, and came. But no, of course there should be a live stream continuing. Yeah.
Yeah, apparently was not completely dead.
Well, no, it makes sense that this session would stream to the live stream.
Well, apparently we gave very good love to the people on the chat. Like everyone was like,
Can you see me? You can hear me, but can you see
oh,
me?
yeah, no, we can see you, we can hear you. So now it's actually perfect. So
Okay. Yeah. So sorry, I didn't think about that. It's kind of early for me.
oh
My
no
brain's
worries. You know, like we had those problems, but earlier in the day, basically. You know, like and then we got used to it, and so
And I was still sleeping.
yeah, there we go. So
I'm gonna watch the recording though.
yeah. So actually, I think we lost potential questions because they got lost in in all the people actually.
Well, and I don't have a record because I killed my whole browser.
Yeah. Okay.
It was
Well,
all Safari.
there we go. But anyway, well, it was a very nice presentation. Thank you. I mean,
Thank you.
In fact,
Thanks for organizing.
yeah, no, of course, yeah, and it was very inspiring. Actually, it's very rare when you can get like that kind of very condensed presentation on this topic. So I think like I enjoyed it.
Well, I was inspired by what I've seen so far. I'm looking forward to digging into the new stuff that's out there.
Yeah, no, that was a very dense day. A lot of information. Like I think that was cool. But yeah, I think I really want to rewatch what just happened. You know, like
I hope somebody uses it in a piece.
yeah, there we go. Yeah.
I want to see it at an ICMC.
Yeah. So yeah, I don't think people have questions as far as I can tell. You know, like,
This was all a plan to get rid of.
yes, there we go. Yeah, that killed it. You know, like
I wanted to go to lunch. Well, you can email me anytime. I'll answer anything.
Actually, there is a question from Dirk,
Okay.
who's saying, can the nonlinear state space models found in nodal decay and the Halters and Zolzer methods be diagonalized in a similar way to the four matrix method?
Well, so if you've got something nonlinear, then you've got, a big problem. So the first thing you do,
That's okay.
I hope we're going to be able to edit this. So I'm going to mute you. I can't. Physical modeling bloopers right here. Okay, I'm gonna not look at you. That'll help me. Okay, all right. Okay, so the first thing you do with a nonlinear system is you just leave the elements of the matrices in whatever form you find them. So you're working with a block diagram of something physical, and you have to just derive the coefficients like I did for the biquad, but that's just a completely general thing that you're working with. And so if it's nonlinear, you don't want to change anything right away. Okay, you have to work with what you have, and that means that diagonalization is very difficult, and it doesn't work always. So the cases that work are when you have the nonlinearity giving you slight perturbations of the modes. A classic example would be a vibrating string, where if you pluck it hard, then the modes go up a little bit. You just get a little bit of sharpening. So a lot of times the nonlinear effect is very subtle. And so you just have to parameterize that some way. And so you can also think in terms of having a matrix that's parameterized, and you find its eigenvectors, and then you move the parameter, find its eigenvector. You have to basically map the eigenvector. You have to track the eigenvectors where they go. So you have to map it out. And you can't always do that because sometimes they'll change radically. Systems can go into different modes. You can have mode bifurcation. You can have all kinds of crazy stuff going on. But most cases of nonlinear musical instruments are weak nonlinearities. String nonlinearities are pretty weak. And so you can get a lot of mileage out of basically just following the modes around. Because what happens is the modes, in linear time invariant systems, the modes don't change. A linear time invariant system has fixed modes. And so whenever the modes are not fixed, you've got some kind of nonlinearity or time variation. And so you just have to track it. And a lot of work has been done along those lines. It's been done. Tero Talonen at HUT comes to mind. Helsinki, his thesis did a lot of that. Estimating the instantaneous length of a string in order to predict the rise in the tension, which allows you to predict the speed of sound increase, which tells you how the modes are moving. So you can do a lot, but be careful. I think I'm calmed down now.
Well, yeah, me too. Yeah.
We used to say, when I was growing up, we called it getting your tickle box turned over.
Sure.
So
there we go. Yeah, I think we don't have more questions actually. So
okay.
As far as I can tell, actually, Stefania is asking if I can repeat your answer.
Go for it.
Yeah, no, I think we're good.
There's no quiz.
Actually, there is one more question. What are your opinions on machine learning for system modeling?
Very interesting. There's a lot of great stuff going on. I'm following it. I'm working with one student in that area, and I'm following everything I can get my hands on. I think it's got a lot of potential. I'm especially interested in using it to, it's the inverse problem that I'm most interested in. For example, as a guitar player who's played in cover bands, who's tried to, imitate everything that's out there, I know what I'm doing, and I think a machine learning system could do it as well, where, I listen to a guitar solo, let's say, and I say, well, I can tell that's Eric Clapton, and he's playing a Strat, and I know that his wah is on, and I know which pickup position he's on. In other words, you just immediately classify so much, right? And so you can get really close to what that is, and now all you have to do is, do a parameter estimation from there. So I think that it's like model inversion without inverting. You just recognize it. It's like if you've heard everything, or heard almost everything, then you can recognize any example and effectively invert the model just because you have memory of what that was. So I'm interested in that kind of tool, a classification tool that will give me parameter calibration from examples. And you can train it on good synthesizer. You can just run your best sampling synthesizer all day long and load it up with examples, or you can build your best model and just fire off random notes with random parameter settings and train it that way. And hopefully it will eventually get to the point where you can play it in Eric Clapton passage and it will tell you all the right settings, and now you've got an automatically calibrated Strat. And of course, there are many other applications. That's just the one that I'm working on now and that I'm really interested in. There's a lot going on out there.
Cool. Well, I think that was it, actually. So.
All right.
Well, thank you so much, Judy.
Off to lunch.
Yeah.
Thank you
for this great presentation, and thank you everyone, actually, because there were a lot of people today, and over 200 people actually registered to the workshop, and I think we had like about always kind of always like 80 people or something like that connected, which is great. So yeah, we really hope you guys had a great time. All the videos that you saw today will be available online. Well, not now because I'm gonna go home now, but tomorrow I'll make sure that everything goes online. And so if you missed something or if you want to rewatch something, you can do it, and it'll all be on the Faust website. So. Thanks, Julius. Thanks to all the other presenters. Thanks, everyone. And
yes, thanks, everyone.
Yeah,
physical modeling in Faust has come a long way.
Yeah, and thanks, and see you next time. Hopefully we can reorganize something like this on a different topic soon. So yeah, bye, everyone. Thanks, Julius.
Thank you.